हरि करना।
So far, we have discussed about what is network and what are the benefits of networking and what are the different types of networks that are available and presently using by the corporates and what is subnet and what are the hardware that a subnet consists of, a router and then a transmission line, and how can we what are the various ways of transferring the data, wireless and wired, satellite, and different types of networks. That's fine, that's all fine. So using this you can send a data from one machine to other machine, but how can these machines understand the data? For example, a host machine sends a host machine sends data from United States of America to the host machine which is present in the Bengaluru. The protocols in India is different. The protocols in American computing is different. So because of that, these systems can't understand. To solve this problem, what we can do? So what we can do is we can use a networking layer. So that's what this module about. So the networking layer is part 2 of module 3 of iDevOps for You course. So here we are going to explore all the layers: the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. So all those layers we will delve into each and every layer, and then we will discuss about each and every protocol that is connected with the each layer in this part of the course. So the first computer networks were designed with the hardware as the main concern and the software as an afterthought. So this strategy no longer works. Network software is now highly structured. In the following section, we examine the software structuring technique in some detail. The approach described here forms the keystone of the entire module and will occur repeatedly and later on. So let's begin with the layers or levels. To reduce the design complexity, most networks are organized as a stack of layers or levels, each one built upon the one below it. The number of layers, the name of each layer, the contents of each layer, and the function of each layer differ from one network to other network. However, the purpose of each layer is to offer certain services to the higher layer. So while shielding those layers from the details of how the offered services are actually implemented. In a simple sense, each layer is a kind of virtual machine. It's each layer is a kind of virtual machine offering certain services to the layer above it, which is above it. I will show it. I will show these things. Okay. Then we will move on to protocol. When a layer n, example, let's take layer 3 on one machine, carries on a conversation with the layer 3 on another machine, the rules and conventions used in this conversation are collectively known as the layer 3 protocol. So basically, a protocol is an agreement between the communicating parties on how the communication should proceed. So as an analogy, when a woman is introduced to a man, she may choose to stick out her hand he in turn may decide to either shake it or kiss it. So bring his hands together to say namaskaram, depending on from which part of world he is. For example, on whether she is an American lawyer at a business meeting, or a European princess at a formal ball, or Indian guru or a sannyasi. So violating the protocol will make a communication more difficult. So if not completely impossible. So what will we do is let's do that layer network illustration. You can see we have two hosts, and this is a 5-layer network illustration. You have a host 1 and then host 2. A 5-layer network is illustrated exactly in front of your eyes. So the entities comprising the corresponding layers on different missions are called peers. The peers may be a software processes, hardware devices, or even human beings. In other words, it is the peers that communicate by using the protocol to talk to each other. So in reality, no data are directly transferred from layer N on one mission to layer N on another mission. Instead, each layer passes data and controls information to the layer immediately below it until the lowest layer is reached. So below layer 1 is the physical medium through which the actual communication occurs. In this illustration, if you see the infographic in front of your eyes, the virtual communication is shown using by dotted lines, and physical communication by solid lines. And if you see between each pair of adjacent layers, layer 5 and layer 4, the interface, it's called layer 4 by 5 interface. The interface defines which primitive operations and services the lower layer makes available to the upper one. When network designers decide how many layers to include in a network and what each one should do, one of the most important considerations is defining clean interfaces between the layers. So doing by providing clean interfaces between the layers in turn requires the each layer perform a specific collection of well understood functions. In addition to minimizing the amount of information that must be passed between layers, clear-cut interfaces also make it simpler to replace one layer with a completely different protocol or implementation. Example, replacing all the telephone lines by satellite channels, because all that is required of the new protocol or implement is that it offers exactly the same set of services to its upstairs neighbor as the old one did. That's it, nothing much. So it is a common it's common that different hosts use different implementations of same protocol, often written by different companies. So in fact, the protocol itself can change in some layers without the layers above and below even noticing it. So a set of layers and protocols is called as a network architecture. A network architecture. So the specification of an architecture must contain enough information to allow an implementation to write the program or build the hardware for each layer so that it will correctly obey the appropriate protocol. Neither the details of the implementation nor the specification of the interfaces is part of the architecture, because these are hidden away inside the machines and not visible from the outside. So a list of protocols used by certain system one protocol per layer is called protocol stack. So if we take the infograph which is on your screen, so how the data transfer takes place from layer 5 to layer 4, then 4 to 3, then 2 to 1, then it will go to the physical medium. What is our physical medium here? The physical medium, and at the same time the protocol for the layer 5 of the host 1 and the protocol of the layer 5 of the host 2 should be same. The protocol of the similar layer in host 1 and host 2 should be same. So then once it reaches to layer 2, then the data will be transferred to the physical medium. The physical medium, it could be a optic fiber or it could be anything. So the physical medium will take the data and it will put it into the layer 1 of the host 2 as it is. So layer 1 and layer 1 of the host 1 and host 2 has the same protocol, so then it can be easily understood by host 2. Then it will go to the layer 2, and then it will go back to the layer 3, then it will go back to the, again it will get back to the layer 4, and finally it will get to the layer 5. So layer 5, a user can see and understand what the data is about. To make more sense of multi-layer communication, let's take analogy. So imagine two philosophers. The third layer, this is the top layer, two philosophers. Basically it's called peer processes. This is, we'll consider it as a layer, third layer, layer 3. See, you can see the number, layer 3. So two philosophers, one of whom speaks Kannada and English, that is Sadhguru. He knows only Kannada and English. And the other philosopher who speaks only Chinese and French. Okay, and this is the top layer. We are taking an analogy. This is a top layer. We can call it as a peer process layer, and the layer name is layer 3. Okay, so now since they have no common language, they each engage in a translator. So here we have a translator, and this is the layer 2. This is also peer process, and then a layer 2 we have a translator. So layer 3 and then a layer 2, two layers. Then each of whom in turn contacts a secretary. So this is a layer 1. So total this is a 3-layer architecture, a 3-layer communication. Let's see how it happens. Now let's try to transfer a message and we'll see what's going to happen. Now what is the problem here? Because philosopher 1, Sadhguru, he wishes to convey a very important message to his peer about yogic karma or karma yoga. To do so, if he passes in English, is it possible for a guy who does not know English and Kannada to understand what he was saying? No, it's not possible. So that is the reason we are using a multi-layer communication process to transfer the data safely, securely, and understandably. Okay, so now here the philosopher 1, that is Sadhguru wishes to convey a message about yogic karma. To do that, basically he knows Kannada and English, so he preferred the English. He passes that message in English. So now across this interface, the 3.2 interface, through this interface he has passed that message, and then it has reached the translator saying yogic karma. Okay, so the translator received this message as yogic karma. Now, the translators have agreed on a neutral language known to both of them. So, both of them, neutral language is French. So, they chosen a French. So, the message is converted to French. That is karma yogiki. Karma yogiki. Karma yogiki. So, the choice of the language is the layer 2 protocol. So what is the protocol that we have used in a layer 2? It is the choice of language and is up to the layer 2 to decide the protocol. So here, through the 2 and 3 interface, yogic karma, the English message has came to layer 2, and layer 2 has a protocol. What is the protocol? Protocol is to translate this English into a common language, that is French. That is the protocol. So this has been executed here. Now the translator then gives the message to a secretary for transmission, for example by email. So now it has reached to the secretary, and the secretary has to send it through email. So here, that's the one, a layer 1. So after the layer 1 is going to use a physical layer called email, and through that is going to sell, he is going to send it. So fax, and then at the rate of karma yogi key. This is in French. So that's the layer 1. So now when the message arrives at the other secretary through the fax, basically that's the uh, physical device that we have used. uh, once it passes to the once the message arrives at the other secretary, it is passed to the local translator. So you can see this step. The message has reached the layer 1 of the host 2. So here, now this guy, what this guy is going to do is, this guy is going to pass that pass that message to local translator, that's which is in French. So then the layer 2 of the host 2 is going to translate that into French and passes it across the 2 by 3 interface to the second philosopher. Note that each protocol is completely independent of the other one as long as the interfaces are not changed. The translator can switch from Dutch to Finnish. So they can choose whatever language that they want, but they have chosen this. So both has preferred a French. Here the protocol is French, and after that, once this guy received that message in French, then he has converted that into Chinese and he has sent it to this guy. So they can go for the common language Dutch or Hindi or anything, but finally the second translator has to he will convert this into the language which is understandable by the this French or this philosopher. So similarly, the secretaries can switch from email to telephone without disturbing, even informing the other layers. So each process may add some information intended only for its pair. This information, the final motto is the information should be passed up to the layer above. That's what the final motto is. The similar way our even the computer based network also works. So now we will look into the actual computer based network. So this flow, uh, the flow which you are going to see only supports a virtual communication and layer 5 layer virtual communication. Okay, so now consider a more technical example. So how to provide communication to the top layer of the 5 layer network that you see in front of your eyes, that figure you can see. Okay, first let's begin. We have two machines. One is source machine and destination machine, and we have 5 layers. It's a 5-layer architecture. So now let's begin. A message capital M is produced by the application process. So the source machine has some WhatsApp or some that sort of application, and that application has produced a message, a message, uh, and it will be passed or it will be given to the layer 4 for transmission. Now a message, now a layer 4 puts a header in front of the message to identify the message and passes the results to layer 3. So the header actually includes the control information such as addresses to allow layer 4 on the destination machine to deliver the message. If you take a few more other examples of control information used in some layers or sequence numbers. In case of the lower layers does not preserve the message order and sizes and times in, and these are some other examples. And in many networks no limit is placed on the size of messages transmitted in the layer 4 protocol, but there is a nearly always a limit imposed by the layer 3 protocol. So now the message with the header has been added and then it will be passed to the layer 3 protocol. So consequently layer 3 must break up the incoming message into smaller units. It's called packets. So prepending a layer 3 header to each packet. In this example, M is split into two parts, that is M1 and M2, and that will be transmitted separately. So layer 2, then it will go to the, then layer 3 decides which of the outgoing lines to use and passes to the packets to layer 2. So now layer 2 adds to each piece not only a header but also a trailer and gives the resulting unit to layer 1 for physical transmission. And finally we are at the we will go to the physical layer. So all this data with the header and trailer and then main message will be transmitted through the physical layer to the destination side. Now at the receiving machine, the message moves upward from layer to layer with the headers being stripped off as it progresses. None of the headers for layers below n are passed up to the layer n. So here the same thing repeats. Here header and trailer will be stripped off. Only message will go up with the S3 and S4. And then once it reaches to layer 3, here adders, one adder will be stripped off, and then message or the main message, because the main message will be broken into pieces now, so that will be accumulated into single message and goes to the layer 4. And then here it's header and then layer, the control information, and then main message will be there. After that, that control information will be stripped off and then only message will be sent to the application. That's how a WhatsApp application works. That's how a message that you have typed will follow all these layers and finally get back to your girlfriend. When you say I love you to your girlfriend or to your mother, so that is the way it goes from your application. That's a layer 5. Then we'll have a layer 3, layer 4, layer 3, layer 2, and then you have a physical device or physical transmission device. Through that again it passes through layer 1, layer 2, layer 3, layer 4, and finally get back to the application. That's a layer 5 where your mother can see, okay, my son said I love you. So the important thing to understand about this figure is the relation between the virtual and actual communication and the difference between the protocols and interfaces. The peer processes in layer 4, for example, conceptually think of their communication as being horizontal using the layer 4 protocol each one is likely to have procedures called something like send to other side or get from other side, even though these procedures actually communicate with lower layers across the 3 by 4 interface and not with the other way around or other side. So the peer process abstraction is crucial to all network design. Using it, the unmanageable task of designing the complete network can be broken into several smaller and manageable design problems, namely the design of the individual layers that we are going to see in coming forth slides. So we'll look into various types of services that we use as layers. So layers can offer two different types of service to the layers above them. So one is connection oriented and other one is connection less service. So in this slide we will look at these two types and examine the differences between the connection oriented and then connection less services. Let's begin with connection oriented service. The connection oriented service is modeled after the telephone system. That was the initial that was the primitive or first network that has been built to talk to someone. You pick up the phone, dial the number and talk, and then hang up. That's how you do with your telephone, correct? What do you do to talk to your friend, a girlfriend, or your parents? You pick up the phone, dial the number, talk to them, and then hang up. So that's what you do. So similarly, to use a connection oriented network service, the service user first establishes a connection and uses the connection and then releases the connection. That's what that's what we call as a connection oriented service. It's basically inspired from the telephone system. The essential aspect of a connection is that it acts like a tube. The sender pushes bits of data in at one end and the receiver takes them out at the other end. In most cases, in most cases the order is preserved so that the bits arrive in the order they were sent. In some cases, when a connection is established, the sender, receiver, and subnet that we have discussed in our previous slides, sender, receiver, and subnet conduct a negotiation about the parameters to be used, such as maximum message size, quality of service required, and other issues. So typically one side makes a proposal and the other side can accept it, so or reject it. It's like proposing a girl. So you can make your proposal, it's all up to her to whether accept it or reject it or make a counter proposal. So uh, if she wants to be with you, she may propose, she may counter propose, she may give you some counter proposal. So a circuit is another name for a connection with associated resources such as a fixed bandwidth. This dates from telephone network in which a circuit was a path over copper wire that carried a phone conversation. Then we will look into a connection less service. What is a connection less service? In contrast to the connection oriented service, connectionless service is modeled after the postal system. How a postal system works: each message or letter, let's take it as a message is equivalent to letter in this example. Each message carries the full destination address, and each one is routed through the intermediate nodes inside the system independent of all the subsequent messages. So there are different names for messages in different contexts. A packet is a message at the network layer. Basically, for us, a packet is it's a message at the network layer. When the intermediate nodes receive a message in full before sending it on to the next node, this is called as a store and forward switching. This is what we call as a store and a forward switching. The alternative way of doing, or the alternative to this, is in which the onward transmission of a message at a node starts before it is completely received by the node and is called cut through switching. So we'll have two types of switchings in connectionless service. One is store and forward switching, and cut it and through switching. That's a cut through switching, and then store and forward switching. Normally, when two messages are sent to the same destination, the first one sent will be the first one to arrive. The first one that you have sent is the first one to arrive. So however, it is possible that the first one sent can be delayed so that the second one arrives first. There is a possibility of that also. So now we have seen connection oriented and connectionless services, both types. The layer can be either connection oriented or connectionless service. So each kind of service further be characterized further be characterized by its reliability. Some services are reliable in the sense that they never lose data. Usually, a reliable service is implemented by having the receiver acknowledge the receipt of each message so that the sender is sure that it's arrived. The acknowledgement process introduces overhead and delays, which are often worth it but are sometimes undesirable. So you can see a connection oriented and then connectionless, whereas a connection oriented, it's a reliable message stream. It's a reliable, and in connection oriented you can have an unreliable connection. That's example voice over IP. So these are the services which can be done through connection oriented and then connectionless, and some of the examples that I have mentioned. A typical situation in which a reliable connection oriented service is appropriate is file transfer. A normal file transfer, a reliable connection oriented service is aptly fit with the file transfer. The owner of the file wants to be sure that all the bits arrive correctly and in the same order they were sent. So very few file transfer customers would prefer a service that occasionally scrambles or loses a few bits, even if it is much faster. So you have two options: either you choose a safe and correct way of sending all the data, or you choose the fastest way of sending and then some data missing or data scrambling. So either you choose one. If you go for the uh, safest and then correct way of sending, then we will go for the reliable connection oriented service, or else you can go for the unreliable datagram. So now a reliable connection oriented service has two minor variations. What are those? The first one is message sequences and byte streams that you can see on the screen. It's exactly in front of your eyes. So message sequence and byte streams. In the former variant, in the message boundaries are preserved. When two 1024 byte messages are sent, they arrive as two distinct 1024 byte messages and never as one 2048 byte message. Whereas in the second case, in the byte streams, what happens is the connection is simply a stream of bytes with no message boundaries. So that is the reason when 2048 bytes arrive at the receiver, there is no way to tell if they were sent as one 2048 byte message or two separate 1024 byte messages or 2048 1 byte message. It's not exactly clear. So that's why first one is a reliable message stream that exactly passes whatever the sender has sent, whereas the reliable byte stream, that we cannot say. Now the next example, if the pages of a book are sent over a network to a photo typesetter as a separate message, it might be important to preserve the message boundaries. Whenever there is a requirement to preserve the message boundaries, it's better to go with the reliable message stream. On the other hand, to download a DVD movie, a byte stream from the server to the user's computer is all that is needed, because message boundaries within the movie are not relevant. Now, for some application, delays, the transit delays introduced by acknowledgements are unacceptable. Basically, if you don't want to have a delay, you want to send it as fast as possible, because if you go with the reliable connection oriented reliable message stream or reliable byte stream service, you will have a delay in sending. So if that is the case, if you don't if the delays are unacceptable, then one such application is digitized voice traffic for voice over IP. So it's like talking on the phone. So voice over through internet protocol is the one such digitized. Basically, this is called as digitized voice over, digitized voice. So in this case, we don't want delay at all, we don't want any kind of delay at all. In this case, we can go for, so it is less disruptive for telephone users to hear a bit of noise on the line from time to time than to experience a delay waiting for acknowledgements. So when you are speaking on the phone, which one would you prefer? A slight delay is better, or a slight noise is better, or a long delay is better? Which is better for you? As a mobile phone speaker, I would prefer to have zero delay, and if there is a slight amount of noise, it's absolutely fine. So that's the reason in this case. Similarly, when transmitting a video conference, having a few pixels wrong is no problem, but having the image jerk with a delay as a flow stops and starts to correct errors is absolutely irritating. So that's why, based on the requirement, the service can be changed or can be used, can be customized. So then we can go for the unreliable. So unreliable meaning it's not acknowledged. That's the only difference. Unreliable doesn't mean it's completely unreliable. The only difference between the reliable connection oriented and the unreliable connection oriented is, the reliable connection oriented, it is acknowledged, and whereas an unreliable connection oriented is not acknowledged. So unreliable connectionless service is often called as a datagram. So here, this is what we are talking about. This is connectionless service. It's a connectionless service, datagram service. In analogy with the telegram service, which also does not return an acknowledgement to the sender despite its being unreliable. It is dominant form in most networks for reasons that will become clear later. So now, to the acknowledged datagram, also we can have the acknowledged datagram service can be provided for these applications too. It's like sending a registered letter and requesting a return receipt. That's what is called as acknowledged datagram. When the receipt comes back, the sender is absolutely sure that the letter was delivered to the intended party and not lost along the way. So text messaging on mobile phones is a best example for this. You just want to get that receipt saying that the message was sent successfully to the intended person. So now still another service is the request reply service. In this service, the sender transmits a single datagram containing a request. The reply contains the answer. So request reply is commonly used to implement communication in the client server model. So what is client server model? Let us look into the client server model in forthcoming slides. So the client issues a request. Of course, the client issues a request whatever he wants, and the server responds to it. This is what we call request reply service. And or else basically the best example is a database query. The best example is database query. So a service is formally specified by a set of primitives or operation. Primitive is nothing but operation available to user processes to access the service. So these primitives tell the service to perform some action or report on an action taken by a peer entity. So if the protocol stack is located in the operating system, as it often is, the primitives are normally system calls. So these calls cause a trap to kernel mode, so which then turns control of the machine over to the operating system to send the necessary packets. So the following are some of the operations that we do for each service. Basically, irrespective of the service, these are the some of the operations or primitives that we do. So the set of primitives available depend on the nature of the service being provided. So the primitives for connection oriented service are different from those of connection less service. So just we'll look into some examples. So one of that such primitive is listen. What listen does is, so block waiting for an incoming connection. And what connect will establish a connection with a waiting peer and accept an incoming connection from a peer and receive it, block waiting for an incoming message and send a message to the peer and disconnect, terminate a connection. Like that, from listening and then connecting, accepting, receiving, sending, and then disconnecting the connection. So this is how a service basically do the operation. These are the operations that will be normally available in a service. So now let us look into various network architectures. So any network that is built using the client server architecture, the devices communicate to the other devices through a central computer is referred to as a server. So this is that server. So the server is a terminal with high processing power, so which provides services for the other computers on the network, and those other computers which take the services from the server are known as client 1, client 2, client 3. Basically they request for data, and then our server serves the data from the database, that to the selected data only, whatever data they request. If client 1 requests a certain amount of data, they will send a certain, the server will route that specific data to this client 1 and then client 2 and client 3 as per their requirements. So now what will we do is, so we will look into uh, the concept or the methodology of how this request and a reply or request and a response interaction takes place in a client and then server. So normally the operations, I just want to explain the operations that takes place in between this client and then a server. So how does it how it happens? So basically these operations we call it as primitives. The correct terminology for these operations are primitive. So these primitives might be used for a request reply interaction in a client server environment. So let's illustrate this using a sketch. For that we are going to sketch a simple protocol that implements the service using acknowledged datagrams. It's acknowledged datagrams. Okay, acknowledged datagram service is the one which we are using. If you do not know what I'm talking about, what is acknowledged datagram, you just watch my previous video. So there you will find it. We have discussed about the different services there. Okay, so now what is going to happen first? First, the server executes listen. First the server executes listen before you request something. First thing, the server executes listen to indicate that it is prepared to accept some incoming connections. That's the first primitive is listen. So a common way to implement listen is to make it a blocking system call. After executing the primitive, the server process is blocked until a request for connection appears. So then next thing is the client. Here is our client. This is our client mission and this is our server mission. As usual, the client mission consists of a kernel, then protocol stack and drivers, and it will be with Linux operating system. And then this is the client process where it's calling system calls. And server mission, it could be our client mission could be a Linux OS, or it could be a Windows, or it could be a Vista, or it could be anything. Whereas but server missions normally comes up with a Linux kernel and then any kind of Linux distribution. It could be Ubuntu, or it could be it could be CentOS. Okay, so now the client process executes connect. Here it is, connect, to establish a connection with the server. Okay, that is our first primitive. So the connect call needs to specify who to connect to. So it might have parameter giving the server's address. So the operating system then typically sends a packet to the peer asking it to connect, as shown in the infographic which is displayed on the screen. So the client process is suspended until there is a response. So then once it gets connected, when the packet arrives at the server, that's through the connection request from the client, the operating system sees the packet. It is requesting a connection, so it checks to see if there is a listener, and if so it unblocks the listener. Then the server process can then establish the connection with the accept call. So using an accept call, accept a response, it accepts the connection request from the client mission. The server mission accepts the connection request from the client mission. So this sends a response to back to the this sends a response to back to the client process to accept the connection. So the arrival of this response is then releases the client. At this point, what happens to the client? At this point, the client and the server are both running, and they have they have established a connection. That's it. At this moment, they have established a connection. So obviously, the obvious analogy that we can take here, the obvious analogy between this protocol and real life is a customer client calling a company's customer service personnel or manager. At the start of the day, the service manager sits next to his telephone in case it rings. He is sitting next to the telephone means he is he is in a listening state. It's a listen primitive. When it rings, so later a client places a call. Client places a call. It is a connection request. It's connect primitive. Then when the manager picks up the phone, it is the connection is established through accept primitive. So that is the analogy that we can take here. So after the connection is established, what's next? The next step is for the server to execute receive to prepare to accept the first request. So normally the server does this immediately upon being released from the listen. So before the acknowledgement can get back to the client. So the receiver call blocks the server. The receive call blocks the server. So this is how the receive primitive comes. But this happens in parallel with the connection request. When it receives the connection request, at that moment itself the receive primitive comes into the picture. So then once once the receive call blocks the server, then the client executes a send send primitive to transmit the request 3, followed by the execution of receive to get the reply. So the arrival of the request packet at the server machine unblocks the server so it can handle the request. So after it has done the work, the server user send to return the answer to the client. So basically this is a reply. It's a reply. It will send a reply to the client 4. So the arrival of this packet unblocks the client, which can now inspect the answer. If the client has additional requests, it can make them know. So now for the final one. So let's look into a small example that's related to this client server architecture. It's not the exact representation of client connection oriented service, but by and large we can get uh, some information from that. For example, this is the API endpoint. So from this I want to fetch some data that's in JSON file. Let me execute this. So I have sent a request. So once the request is sent, and then we got the response, but that's what we see here. But whereas behind the screen in the back end, a service, a primitive service, and then primitives takes place, and then because of each operation we could see the final response. How this happens, that we can see if you go here. So this part you can see the event. So first what had happened is socket initialization. So after the socket initialized, it's basically one is in the one part is in waiting. It's basically, what do we call it as, um, one part is listening, and that our server is listening. And then once you initialize your connection request, basically connect a request, when you initialize from your side, then obviously DNS lookup, and then once DNS looked up, then TCP handshake, then SSL handshake, then finally after all these activities accepting the response, and as we have requested a specific kind of information from this endpoint employees, so that has been accepted. Once that is accepted, so then the transfer started. So the response has been started, and finally it's been downloaded, and then it got disconnected. So this is the event. It's a single event, and that is how a service works behind the hood. Not exactly the same that we have seen. It's a different kind of service. However, the process by and large goes similar to the service that we have seen in our slides. And as we have discussed in our layers, so body is the main data and headers is the one which navigates the data through different layers. So body is 636 bytes, whereas headers is 472 bytes. This is how it works. Without the headers, it is very difficult to navigate that body to the different clients. So now let us again get back to the our second kind of architecture. The second kind of architecture that we have here is a P2P architecture. P2P architecture or peer-to-peer architecture. So what is peer-to-peer architecture? On a network built using the peer-to-peer architecture, there is no specific distinction exists between a client and a server. That's the main difference, a client and server. So it's not a client and server architecture. Any node, as there are a lot of systems will be there, a lot of servers are there, clients are there. So any node can provide a service as well as send a request for a service from another node on the network. It's kind of peer-to-peer architecture. It is not like client server. One server will be there and is going to serve everybody. No, not like that. Anybody can send to anybody. Anybody can serve to anybody. So that's anybody. That's what the peer-to-peer architecture. So this is how a peer-to-peer architecture looks like. This is a client. It's not exactly a client and server, but at when this PCA requests for data, then it will become a client, and when another PCB, when this responds with the data, when this sends the data, it will become a server. Whereas when PCB requests for a data, then PCB will become a client and then PCA will become server. So this is how it interchanges and intertwines their roles. So services and protocols are distinct concepts here. So the distinction is so important that we emphasize it again here. So a service is set of primitives. Primitives are nothing but operations that we have seen in the previous example that a layer provides to the layer above it. So the service defines what operations the layer is prepared to perform on behalf of its users. So, but it says nothing at all about how these operations are implemented. So a service related to an interface between two layers, with the lower layer being the service provider and the upper layer being the service user. So in this, so a protocol, so in this what we see is in peer-to-peer architecture, it doesn't matter. It is neither one system is specifically a server nor other system is specifically client. So both all the systems, all the computers which are in this network, all the entities which are present in peer-to-peer architectures can either act as a server or either or act as a client based on the requirement, based on the need of the hour. So now let's look into OSI reference model analogy with the postal system. So let's use a postal analogy to understand OSI better. So let's get back to the OSI one more time and just read through the layers. What all layers we have? So application, presentation, session, transport, network, data link, and physical. These are the 7 layers. So now let's take the postal system analogy to understand these 7 layers better. So let's OSI the postal analogy. As usual, the top layer is the application layer, the higher layer is the application layer. So in application layer, what do? So you have write, okay, I'm taking this example. I have written, or you have written, a 30-page love letter to your girl or boyfriend, the one she might be living or residing in a foreign country. It could be United States of America, or it could be European countries such as Sweden, or maybe Germany, UK, England, whatever it could be. Okay, so then, so that whatever that you write in your letter, or the letter, the 30-page letter itself is your application layer. That is your application layer. So then what we have is a presentation layer. What is presentation layer? Translate the letter so your girl or boyfriend can read it. Basically, it is, she's living in Sweden. She does not know uh, English. You are living in Karnataka. You do not know English or Swedish language. So you have written your love letter in Canada, and she does not know Kannada. So you have used a presentation layer or a translator. So the letter has been translated into Swedish language directly from the Kannada language, so that your girlfriend can read it, her boyfriend can read it. So that's our presentation layer. That's what a presentation layer does. Okay, so then after the translation we have a session layer. So in session layer, ensure the intended recipient can receive the letter. So that's what the session layer do. So then after session layer we have a transport layer. So in transport layer, now it is time to and separate a number pages, each page, like registered mail, and then track delivery and request another package if one is lost or damaged in the mail. So you separate and number each pages, and then you put it into one package. So and make sure, if anything got lost or damaged, you can easily uh, you can easily basically get to know that. So that's the transport layer do. And then we have a network layer. In network layer, postal center, then the hardware stuff comes, then the actual action begins. The postal center sorting letters by zip code. So in transport layer you have put everything, so and all done. So now it's time for the postal center to take care of rest of the things. So postal center will sort your letters by zip code to route them closer to the closer destination. So then after the network layer, it's a data link layer. So now uh, we'll use some local post office determining which vehicles to deliver letters. So that's what a data link here. Sometimes the postman itself, he carries he brings the letter, and sometimes they use minivans to carry those letters. So that's basically data link. It's linking final receiver with the post office. So that's like kind of a link. So that's why we call it as a data link. And then physical layer, that is the final physical truck, plane, rail, auto, etc., whichever way. If sometimes the postman itself carry the one, so in that case he could be the physical layer. So the one which carries letter between the stations. So this is how, when you want to send a letter to your girlfriend or boyfriend who resides in Sweden, basically it's a sender and then a receiver. It will follow through 7 layers. Ideally it should follow through 7 layer. First application is writing a a love letter. Your love letter is your application layer. Then translating into Swedish is a presentation layer. Then make sure intended, it's basically you ensure the intended recipient can receive the letter. For that, what you do, you attach your information, attach your recipient information on your postal card. Then transport layer, so here basically you will separate the number of pages and like registered mails, tracks delivery, and then request another package if one is lost or damaged in the mail. And then after that, the actual hardware action starts. Then network layer, postal center sort out the letters based on the zip code, and then they'll route to the closer destination. Then data link comes into the picture. The local post office will determine which is the best way to send or deliver those letters. And then the final layer is the physical layer, where the physical trucks or whichever way or whichever mode you can use to deliver that letter. So that's how a postal analogy can make much sense in understanding OSI, open system interconnection reference model. So and this model, if you just want to take an email or any web application, WhatsApp as example. So your application layer is your WhatsApp. There, once you type a message, then a presentation layer will exist, and it will convert that English alphabets or English words into HTML. And then once it's converted into the HTML, this presentation layer translates, because the physical layer cannot understand the English letters. So initially it will be converted into HTML, and then after the session layer will note down the time and everything at what time, and then there the session layer will make sure whom to be sent, so the recipient and where it to be sent, that all will be noted in the session layer. Then the transport layer comes into the picture, and then it will bifurcate the complete message, whatever message that you have spent, that you have typed. Maybe it may be of 30 or 40 lines. All will be bifurcated into sub certain pieces, and then each will be attached with the headers. So you will have a body header, body header, body header. Based on the time and based on certain parameters, it will divide, and it will divide into different parts. And after that, it will go to the network layer. Again, the main action starts there. It find out the which subnet to be sent, and then in that network layer, all this whatever pieces have been broken into body and then headers. So this one will be directly converted into the frames. So frames, and after that it goes to the data link layer. In data link layer, each frame will be converted into sorry. So after the transport layer, it will be converted into packets. Sorry, that's my fault. It will be converted into the packets, and then after the network layer, the packets will be converted into the frames. So each frame is equivalent to 100 bits, or maybe 1000 bytes, 1000 bytes. So after that, these frames will be converted into bits, zeros and ones. These zeros and ones can be then converted into the light pulses or analog signal, that is that can be sent through the optic fiber to the host machine. And then same cycle will repeat, even same flow will repeat even the other host B side. There again, physical layer, zeros and ones, and then data link, it will be converted into the frames, and then frames will be converted into the packets, and then packets will be converted into the different types of um, basically into different bodies and headers. And then finally, based on the sessions that were given in previous from the host A, so with the same parameters it will be absorbed, and after that it will go to the presentation layer. In presentation layer, all these data will be converted into HTML code, and then when it goes to the application layer, this HTML will be converted into English, and then finally you can read in the other guy's WhatsApp message. So now that we have discussed the layered networks in the abstract, now it's time to look at some examples. So now we are going to discuss two important network architecture reference model. One is the OSI reference model and other one the TCP or IP reference model. Then what is the difference between OSI reference model and TCP IP reference model? To understand this better, so let me explain about molecular theorem or gas mechanics. So in gas mechanics, what we have is you will have an ideal gas. What is an ideal gas? Ideal gas is the one which exactly follows the law PV is equals to nRT. Pressure times volume is equals to number of molecules times universal gas constant times temperature. If that exactly follows that law, no, actually there is no gas that exactly follows that law. So that's why if anything exists such a way, that's called an ideal gas. So if anything that behaves close to this PV is equals to nRT, also we can say ideal gas, but there is no such gas. That's why it is just ideal. It is just ideal, it doesn't exist. Whereas a real gases, there will be huge difference when you do the calculation. Pressure times volume is equals to nRT. So that's the reason we have ideal gas and then a real gases. So real gases doesn't follow the PV is equals to nRT. Similarly, if you come to the fluid mechanics, in fluid mechanics also we'll have an ideal fluid and then a real fluid. Ideal fluid is the one which exactly follow the laws of mechanics, laws of fluid mechanics, whereas the real fluid, they basically doesn't exactly go hand in hand with the fluid mechanic laws. For example, if one law is applicable, then another law can be applicable directly. So that is the reason. So when you do the fluid mechanic calculation, there will be a lot of confusion. So I hope I don't want to enter into fluid mechanics now. Okay, so now you got the difference. An ideal gas and a real gas, an ideal fluid and a real fluid, and a reference model and an actual model. A reference model and an actual model. So reference model is the OSI reference model and then actual model is the TCP or IP reference model that we are actually applying to our systems. So what is a reference model or OSI? OSI is like an ideal model. So we prefer to have these many layers, and this is like a reference, and whatever model that you want to build after that should should at least have these many layers or can have lesser than this, but it should by and large should follow this reference model. It's like a reference. It's like a reference to the a real model, like ideal gas, real gas, ideal fluid, a real fluid. Similarly, a reference model and an actual model. OSI a reference model is the ideal one, and TCP or IP reference model is the actual model. So although the protocols associated with OSI model are not used anymore, so the model itself is actually quite general and still valid, and the features discussed at each layer are still very important. So the TCP or IP model has the opposite properties. The model itself is not of much use, but the protocols are widely used. For this reason, we will look at both of them in detail. Also, sometimes you can learn more from failures than from successes. So, OSI reference model and then TCP IP reference model. So, now let's, of course, there are plenty of other network models also, but we are going to discuss this. So the OSI reference model is the standard one, which is started first, and after that there were a lot of models that were built. Now let's begin with the OSI reference model. The OSI model, basically minus the physical medium, is based on a proposal developed by International Standards Organization ISO as a first step toward international standardization of the protocols used in the various layers. It was revised in 1995, day 1995. So the model is called ISO OSI. OSI means Open System Interconnection Reference Model, because it deals with connecting open systems, that is, systems that are open for communication with the other systems. So we will just call the OSI model in short. So OSI model is nothing but Open Systems Interconnection Reference Model. So the OSI model has 7 layers. The principles that were applied to arrive at the 7 layers can be briefly summarized as follows. The first principle is a layer should be created where a different abstraction is needed, and each layer should perform a well-defined function. And third, the function of each layer should be chosen with an eye toward defining internationally standardized protocols. And the fourth, the layer boundaries should be chosen to minimize the information flow across the interfaces. And the fifth, the number of layers should be large enough that distinct functions need not be thrown together in the same layer out of the necessity, and small enough that the architecture does not become unwieldy. So note that the OSI model itself is not a network architecture, because it does not specify the exact services and protocols to be used in each layer. It just tells what each layer should do. However, ISO has also produced standards for all the layers, although these are not part of the reference model itself. So each one has been published as a separate international standard. So the model is widely used, although the associated protocols have been long forgotten. So what will we do is, as we know, this is an ideal model, and this is a reference model, and these protocols that belongs to this model have have been forgotten, have been lost, forgotten completely. So have been long forgotten before only. So that's the reason. But still exploring and expounding the each layer of this model will give you a complete 360 degrees 360 degrees view on reference models. Then it would be very easy to understand TCP or IP model. So that's the reason we are going to explore each and every layer of OSI, that's Open System Interconnection Reference Model. So how many layers it consists of? 7 layers. The application is the first layer, then data from application goes to the presentation layer, and application will have application protocol. Then layer number 6 is presentation layer. From presentation layer it will go to the session layer, that is layer number 5, and session layer holds session protocol. Then from session layer it goes to the transport layer, and transport layer number is layer number 4, and it holds a transport protocol. Then from there data travels to network layer, and network layer number is layer number 3, and it holds the most important, the actual hardware starts here. Through this network layer, a communication subnet boundary. Basically, this network layer is communication subnet boundary. Then one network will be connected with the other network. through the communication subnet boundary. And then the next layer that we have is data link layer. It's the layer number 2, and at the data link layer we will have a data link architecture. So this data links basically connect each other, and finally it enters the layer number 1, the physical layer. So the physical layer, it's nothing but transmission lines and then routers. So it both sides, host A and host B, both is going to have this one. So this the overall, the three layers: network, data link, physical layers, protocol, we call it as a internal subnet protocol. So, and the whole stuff we call it as a network layer and host router protocol. So only in the network layer we will have a host router protocol, and inside each will have a internal subnet protocol. But actually from network layer the actual hardware starts, the subnet starts, and then data links, and then physical layers such as router, and then transmission lines comes into the picture. So these are the seven layers OSI, open system interconnection reference model consists of. So now let us try to understand each and every layer of reference model, of OSI reference model. We'll begin with the first layer, that is layer 1. I'll begin with the layer 1. That is the physical layer. Then what is the physical layer? Okay, so the physical layer is concerned with transmitting raw bits over a communication channel. So the design issues have to do with making sure that when one side sends a 1 bit, so this is the name of the unit exchanged, name of the unit that will be exchanged, that is bit at the physical layer. When one side, that's a host A side, sends when a host A side sends a 1 bit, it is received by the other side as 1 bit, not as 0 bit. So typical questions here are: what electrical signals should be used to represent a 1 and a 0? How many nanoseconds a bit lasts, whether transmission may proceed simultaneously in both directions, how the initial connection is established, and how it is torn down when both sides are finished. So how many pins network connector has and what each pin is used for. So these design issues largely deal with mechanical, electrical and timing interfaces, as well as the physical transmission medium which lies below the physical layer. So then we will move on to, basically this is the physical layer. Here we'll have physical layer host router protocol here in next, and then we will move on to the layer 2, layer number 2, that is the data link layer. The main task of the data link layer is to transform a raw transform a raw transmission facility into a line that appears free of undetected transmission errors. It does so by masking the real errors so the network layer does not see them. So it accomplishes this task by having the sender break up the input data, whatever input data that comes, so that will be broken up into data frames. Typically a data frame is equivalent to typically a few hundred or a few thousand bytes, and transmit the frames sequentially. So if the service is reliable, the receiver conforms correct, because we have discussed so many types of services in our previous slides. If the service is a reliable type, the receiver confirms the correct receipt of each frame by sending back an acknowledgement frame. So here the unit is frames. So you can see Here bits, it's basically zeros and ones, but one level up it is frames. Frames will can have either few hundred or few thousand bytes. It could be 100 or 1000 bytes. Okay, so then we'll have the third layer, layer number 3, that is the network layer. The network layer controls the operation of the subnet. That's what I'm saying. The physical hardware starts. A key design issue is determining how packets are routed from source to destination. So routes can be based on static tables that are wired into the network and rarely changed, or more often they can be updated automatically to avoid failed components. So they can also be determined at the start of each conversation. For example, a terminal session such as login to a remote machine. Finally, they can be highly dynamic, being determined a new for each packet to reflect the current workload. So when a packet has to travel from one network to another to get to its destination, many problems can arise. The addressing used the addressing used by the second network may be different from that used by the first one. So the second one may not accept the packet at all because it is too large. So the protocols may differ and so on. It is up to the network layer to overcome all these problems to allow the heterogeneous networks to be interconnected. So here the data is in packets. The name of unit exchanged is packet. So after that we will move on to the fourth layer, that is the transport layer. The basic function of the transport layer is to accept data from above layer and split it up into smaller units if need, so and then pass these to the network layer and ensure that the pieces all arrive correctly at the other end. So furthermore, all this must be done efficiently in a way that isolates the upper layers from the inevitable changes in the hardware technology over the course of time. So the basic function of the transport layer is to accept the data from the above layer and then split it up into smaller units and then pass it to the network layer, and also to ensure all the pieces have arrived correctly. So here, so transport layer, the unit is TPD, transport data units, a TPD. So it's a transport protocol. So this one is going to break up your data and so for that, so based on time, based on some other the sender name, based on the address, based on these factors, it will break up the complete message and it will attach in a headers, and then it will pass that to the network layer and the network layer will convert that into packets. Okay, so then we have the fifth layer, that is a session layer. So the session layer allows users on different machines to establish sessions between them. So sessions offer various services include dialogue control, keeping track of all turn. It is to transmit token management, preventing two parties from attempting the same critical operation simultaneously, and synchronization, checking, checkpointing long transmission allow them to pick up from where they left off in the event of a crash or subsequent recovery. It's a session protocol DU. So that's what the SP DU. So then it's basically takes care of the sessions, and after that what we have is the layer number 6 is the presentation layer. The presentation layer, unlike the lower layers which are mostly concerned with moving bits of data around, the presentation layer is concerned with the syntax and semantics of the information transmitted. In order to make it possible for computers with different internal data representations to communicate, the data structures to be exchanged can be defined in an abstract way along with a standard encoding to be used on the wire. So the presentation layer manages these abstract data structures and allows higher level data structures to be defined and exchanged. So here we'll have a presentation protocol, PPDU as the name of unit exchanged, and then the last but not the least, layer number 7, the application layer. The application layer contains a variety of protocols that are commonly needed by users. One widely used application protocol is HTTP, that is Hypertext Transfer Protocol, which is the basis of the World Wide Web, WWW. So when a browser wants a web page, it sends the name of the page it wants to the server hosting the page using HTTP. So the server then sends the page back. Other application protocols are used for file transfer, electronic mail, and network news. So before we move on to the analogy, so I just want to explain, I just want to give a quick summary about the reference model. That's OSI reference model. So application layer is the one which presents the message. If you take the WhatsApp example or mail, if you take the mail, whatever you see on the screen, that is taken care by the application layer. And then we have a presentation layer. Presentation layer is the one which converts the English language into basically another protocol that we use. If it is HTML protocol, if HTML language, if it is something else, then once it's been converted into that, now based on the sessions, the data will be broken into different pieces in the transport layer. Once it's been broken into different pieces in the transport layer, and then each of that message body has been given with the headers, and then that headers and then message body will go to the network in packets, and then these packets will be further broken into frames. That frame can be 1000 bytes or can be 100 byte or can be 1000 bytes. Then after that, these frames will finally split it into bits, zeros and ones, and these zeros and ones will be converted into basically a light signal in optic fiber, and it travels across the optic fiber, across the seas and across the continents, and finally goes to the physical layer, goes to the data link of the other side of the host B mission, and then same repeats, and it will become converted into frame and then packets and then TPDU and then SPDU, and then it will convert into HTML, and then HTML will be converted into English message that we can see and read on your computer. So now let us look into the actual model, real model, that is the TCP / IP reference model. So let us now turn from the OSI, that is Open System Interconnection reference model, to the reference model used in the grandparent of all wide area computer networks, that is the ARPANET. So and its successor, the World Wide Internet. So the ARPANET was a research network sponsored by DoD, that is US Department of Defense. It eventually connected hundreds of universities and government installations using leased telephone lines. When satellite and radio networks were added later, the existing protocols had trouble interworking with them. So a new reference architecture was needed. So thus, from nearly the beginning, the ability to connect multiple networks in a seamless way was one of the major design goals. So the architecture later became known as the TCP forward slash IP reference model after its two primary protocols. Based on its primary, it was named after their two primary protocols, that is TCP forward slash IP reference model. So it was first described by Cerf and Cahan in 1974 and later refined and defined as a standard in the internet community by Braden at 1989. So the design philosophy behind the model is discussed by Clark in 1988. So and then it was given the DOD, that's defense of uh, mm, and then Department of Defense of United States of America's worry that some of its precious hosts, routers and inter-network gateways might get blown to the pieces at a moment's notice by an attack from the Soviet Union. So another major goal was that the network be able to survive loss of subnet hardware without existing conversations being broken off completely. So, in other words, the Department of Defense wanted to, sorry, United States of America's Department of Defense wanted connections to remain intact as long as the source and destination machines were functioning, even if some of machines or transmission lines in between were suddenly put out of operation. So furthermore, since application with divergent requirements were envisioned, ranging from transferring files to real-time speech transmission, a flexible architecture was needed. So these are the fundamental reasons that led to bring this new architecture, new reference model, that is TCP IP reference model by ARPANET. And it's not just ARPANET, there are a lot of students and colleges has worked with this. So we know an ideal model is OSI. It consists of 7 layers: application layer, presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. So this is an ideal model, ideal reference model. OSI is an ideal reference model. So now what is the actual reference model that is made is TCP forward slash IP. This is the actual reference model. So how many layers it will consist of? Let us see. Let us see. Application layer does exist. Oh, so what is application layer? Here the application layer. So the TCP IP model does not have session or presentation layer. So no need for them was perceived. Instead, applications simply include any session and presentations functions that they require. So experience with OSI model has proven the view correct. So these layers are of little use to most applications. On top of the transport layers, on top of the transport layer is the application layer. So it contains all the higher level protocols. It consists of the early one included virtual terminal protocol, that is telnet. Even though till they use this telnet protocol, and then FTP, that is file transfer protocol, even now we use it. Then SMTP, that is electronic mail protocol. and many other protocols have been added to this over the years, and it also includes domain naming system DNS protocol for mapping host names onto their network addresses, and then HTTP, the protocol for fetching pages on the world wide web, and RTP, the protocol for delivering real-time media such as voice or movies. So most of the protocols has been included in application layer only, and the presentation layer and then session layer has been completely eliminated. It does not have presentation and session layer. So then we'll have the transport layer. So the layer above the internet layer in the TCP or IP model is is usually called the transport layer. It is designed to allow peer entities on the source and then and destination hosts to carry on a conversation just as in the OSI transport layer. So two end-to-end transport protocols have been defined here. The first one is TCP. TCP is Transmission Control Protocol. TCP is a transmission control protocol, is a reliable connection oriented protocol. It's not the connection less, it's a connection oriented protocol, and that too it's reliable. That means it will provide an acknowledgement that the receiver has received the data packet that we have sent. So it's a reliable connection oriented protocol that allows a byte stream originating on one mission to be delivered without receiving uh, without error on any other mission in the internet. So it segments the incoming byte stream into discrete messages and passes each one onto the internet layer at the destination. The receiving TCP process reassembles the received messages into the output stream, and TCP also handles flow control to make sure a fast sender cannot swamp a slow receiver with more messages than it can handle. So this is one protocol that is widely used. However, there is a second protocol in this layer, that is UDP. This is user datagram protocol. Of course, this is unreliable. One is reliable and other one is reliable. One has their own benefits, and we have discussed the uh, positives and negatives of these services before only. So UDP is a user datagram protocol. It is an unreliable, so it's a connection less protocol for applications that do not want TCP's sequencing or flow control and wish to provide their own. So it's also widely used for one shot client server type request reply queries and applications in which prompt delivery is more important than accurate delivery, such as transmitting speech or video. The relation of IP, TCP, and UDP, these are all IP is Internet Protocol, TCP is the Transmission Control Protocol, and UDP is the User Datagram Protocol. All can be seen in your screen exactly on top of your in front of your eyes. So since the model was developed, IP has been implemented on many other networks. So then the next layer in pipeline is the internet layer. The internet layer is the linchpin that holds the whole architecture together. So it is shown in the infograph as corresponding roughly to the OSI network layer. So its job is to permit Its job is to permit hosts to inject packets into any network and have them travel independently to the destination, potentially on a different network. So they may even arrive in a completely different order than they were sent, in which case it's the job of the higher layer to rearrange them if any order delivery is desired. So let's go for the analogy of the TCP IP proto IP model with the mail system analogy. So the analogy here is with the mail system. It begins with writing a sequence of letters. So that is our application layer. So now a person can drop a sequence of international letters into a mailbox in one country, and it will, and with a little luck, most of them will be delivered to the correct address in the destination country. So drop these letters into a mailbox in India, and we are hoping that it's going to be delivered into United States of America or whichever country, destination country you are expecting to be delivered. So then that's our transport layer. So now the letters will probably travel through one or more international mail gateways. That's what the internet is. We do not know exactly through which way it goes. It doesn't matter. It can take a flight, it can take waterways, it can take any way. It doesn't matter. So that's why the letter will probably travel through one or more international mail gateways along the way. But this is transparent to the user. So furthermore, each country, that's each network has its own stamps, preferred envelope sizes, and delivery rules is hidden from the users. So here the internet layer defines an official packet format, and protocol is called IP, that is Internet Protocol. So Internet Protocol plus a companion protocol called ICMP, Internet Control Message Protocol, that helps it function. So the job of the internet layer is to deliver IP packets where they are supposed to go. So packet routing is clearly a major issue here, as is congestion. So though IP has not proven effective at avoiding congestion. And then finally we'll have the physical layer. So through the physical layer it's going to be but that physical layer also will be taken care by the internet only. So then the last layer, the fourth layer of this, you can see this internet layer has two protocols, that is IP and then ICMP. IP is Internet Protocol, and then ICMP is Internet Control Message Protocol. So, and finally what we have is the link layer or the physical layer. So all these requirements led to the choice of all these requirements led to the choice of packet switching network based on the connectionless layer that runs across different networks. So the lowest layer in the model is the link layer, so that we are missing the link layer. And the link layer describes what a link such as a serial lines with classic Ethernet must do to meet the needs of this connection less internet layer. It is not really a layer at all in the normal sense of the term, but rather an interface between hosts and transmission links. So early material on the TCP or IP model has little to say about it. So if you see it, these are the total four layers that are available in TCP IP actual real reference, model, and then each layer has a different protocol. In application layer, we have HTTP, SMTP, RTP, DNS, and then for link layer, we have DSL, SONET, 802.11, Ethernet. These are the basically standards that we have seen. Ethernet standard 802.8 and 802.11 is wireless, that's Wi-Fi, and 802.3 is some other one. So we have DSL, that is also related to the connection only, internet connection, and then SONET. So these are the different protocols that are specific that are related to the each layer of the TCP or IP, and you can see the TCP or IP, the mail system analogy also here. Look into the architecture of the internet and how does the data reach you. So have you ever had this question in your mind? If not, at least you get it now, you have it now. So because I'm going to explain how does the data reach you, how does the YouTube video that you are presently streaming in YouTube or watching in YouTube or viewing in YouTube reach you, how it is reaching you. So the architecture of the internet has also changed a great deal as it has grown explosively. So in this slide, I will attempt to give a brief overview of what it looks like today. So the picture is complicated by continuous upheavals in the business of telephone companies, telcos, cable companies, and ISPs that often make it hard to tell who is doing what. So one driver of these upheavals is telecommunications convergence, in which one network is used for previously different uses. For example, in recently the recent development is a triple play. Triple play. What does the triple play mean? So one company sells you telephony, TV, and internet service. So three services will be sold by one company through one subscription. So that is called triple play. So over the same network connection, on the assumption that this will save your money. Consequently, the description given here will be of necessity somewhat simpler than reality, and what's true today may not be true tomorrow. So let's explore and expound the internet architecture or the architecture of the internet. So let's begin with the various subnets in America, and then if you look into the America subnet, this is one subnet. So this subnet consists of various routers, and then to transmit a light signal, we have optic fiber with a certain standard that could be cat 5. Normally these are called backbone. The optic fiber lines, transmission lines that we use in subnet are known as backbone. So a router and a backbone and together makes it a subnet. So basically, as this is subnet, so we call this as a tier 1 ISP. So if you want to tap in network from here, so that's a tier 1 ISP. The one who provides this service provider are called as a tier 1 ISPs, tier 1 internet service provider, and this is America's subnet. Similarly, Europe has their own subnet, that is again routers and then backbones, and then it makes up one subnet that belongs to Europe. And similarly, China has their own subnet. It makes routers and then transmission lines collectively makes up the China's subnet. Then same goes with India. India has their own subnet and then routers and then transmission lines. And here, if you see, America's internet service provider could be what some other provider, some other enterprise, and here in Europe somebody, in China somebody, in India somebody. It is not same. In India it could be Geo or somebody else, and then in America it could be somebody else. That's what I'm saying. So no, these backbones are these subnets are owned by different service providers. The one who is owning uh, the one who's owning the mm, subnet in America is not maybe he is not going to own subnet in India. He can, but we're not sure. Somebody else will have a subnet in India. Okay, so these are the subnets in America, Europe, China, India. Then basically to connect from one subnet to other, we'll use peering at IXP. So it's internet exchange point. So this is called basically until unless if you don't connect one subnet with the other subnet or one network with the other network, so it's impossible to transfer or transmit data from one network to other network. So that is the reason we connect one network to other through peering at IXP, peering at internet exchange point. So each subnet or each network will be connected through this. You can see America's network with the Europe, America's with the China, America with the China, and then China with the India. So ISP networks may be regional, national, or international in scope. So we have already seen that their architecture is made up of long distance transmission lines that interconnect routers at POPs in different cities that the ISPs serve. So this equipment is called the backbone of the ISP. If a packet is destined for a host served directly by the ISP, that packet is routed over the backbone and delivered to the host. Otherwise, it must be handed over to another ISP. So ISPs connect their networks to exchange traffic at IXPs. These are called internet exchange points. So the connected ISPs are said to peer with each other. So the big picture that is shown in the slide, uh, let us examine this figure. Let's examine this figure piece by piece, starting with a computer through which you are watching the video, most probably from India. Let us consider that you are watching this video from India. So now to join the internet, the computer is connected to an internet service providers or simply ISP. So from whom the user purchases internet access or connectivity. So here in this case, the method used to send signals over the cable TV like DSL. So this is a way to reuse existing infrastructure So in this case, otherwise unused cable TV channels. So the device at the home end is called a cable modem. I think most probably you might have used, I think 2000 kids might have used this one, cable modem and then cable. So the device at the home end is called the cable modem, and the device at the cable head end is called as CMTS, cable modem termination system. Okay, so then, so Geo, Airtel, VI, that's Vodafone Idea, BSNL are top 4 ISPs in India. So by total subscriber base, and Rail Railtel Corporation of India is a state-owned ISP with the pan India optic fiber network along railway track. So this is one way of connecting or accessing other networks through internet, that is cable modem, and then the one which we use to connect with the router or to the CMTS, that is cable modem termination system. We call it as a cable. So uh, this lets the computer exchange packets with all of the other accessible hosts on the internet. The user might send packets to surf the web or for any of 1,000 other users, it does not matter. So there are many kinds of internet access, and they are usually distinguished by how much bandwidth they provide and how much they cost. But the most important attribute is connectivity. So now let us look into these various types of internet connectivities that we can have at the present time. So now let us take one example. One of my friend is living in Europe. So this is the guy who's in Europe. His name is Raki or Ramki. So now we'll see what are the ways that he connect an internet. He connect an internet connection to your home, or what are the ways he can connect with their ISP network, that is internet service provider network. So the first one is a common way to connect to an ISP is to use the phone line to your house, in which case your phone company is your ISP. And the second one is DSL. DSL short for digital subscriber line. Digital subscriber line. So DSL reuses the telephone line that connects to your house for digital data transmission. So in this case, the computer, so you can see this, in this case that you will have a DSLAM, this is the main one, and then DSLAM is digital subscriber line access multiplexer. The computer is connected the computer is connected to a device called DSL modem. Here it is, it's a DSL modem, and that converts between digital packets and analog signals that can pass unhindered over the telephone line. At the other end, a device called a DSLAM, Digital Subscriber Line Access Multiplexer, which converts between signals and packets. So this is one type of connection. So in this connection, basically we call it as it's basically the simplest way. Many of the 2000 kids or 2010 at that time, they might have used this widely. It is called you have to take a telephone connection to have a internet. So that's why you take a telephone connection internet. Basically, we are using a telephone line for internet. So at your home, you will have a DSL modem, and then the cable that we get it from DSLAM is known as DSL, and then on the main side we'll have DSLAM. That's a digital subscriber line access multiplexer. So the best examples, the one who provides this kind of DSL based internet service are Century Link, AT&T, Earth Link, Verizon Wireless. So these are the companies. Basically, these are a few examples of DSL internet service providers. So then we will look into another type of connecting internet to your home, to your laptop. That is dial up. So I have one more friend. His name is Krish. He also lives in Europe, and he also wants to connect with he wants to get connection of internet. So how can he do it? So now let's see what way and what method he has chosen. The method he has chosen is dial up. So several other popular ways to connect to an ISP is a higher bandwidth way to use the local telephone line than to send bits over a traditional telephone call instead of a voice conversation. So is called as dial up, and done with a different kind of modem at both ends. The word modem is short for modulator, demodulator, modulator, and demodulator, and refers to any device that converts between digital bits and analog signals. So this is our dial up, and this is our router, and this is the way we connect with the dial up. And then I have one more friend who he also lives in Europe, and he wants to have a connection. He also wants to have a connection, and let's see what kind of connection he will get for his laptop for an internet connection. So now this time uh, so he has a problem. As thus far we have seen DSL based connection, and then dial up to connect. Two types of connections we have seen. So now DSL and cable provide internet access at rates from a small fraction of a megabyte per second, it's MB per second, to multiple megabit per second. So megabit per second to multiple megabit per second depending on the system. So these rates are much greater than dial-up rates, so which are limited to 56 kbps. So if you go for the dial-up, it is just 56 kbps because of narrow bandwidth used for the voice calls. So internet access at much greater and dial-up speeds is called the broadband. So the name refers to broader bandwidth that is used for faster networks rather than any particular speed. When they say broadband, it's better than the dial-up. That's it. So now this guy, he has three options. One is through cable, other one is through DSL, other one is to dial up, out of which he, after looking at the speeds, one is broadband, these two are broadband, and then through cable it's a narrow band. After looking at all three options, he wants to go with, he was looking for an option which gives much more broader band network, a much more faster speed, a much more better network. So then he found, this is the guy, then he found a FTTH, that is fiber to the home. So the access method the access methods mentioned so far are limited by the bandwidth of the last mile or last leg of transmission, and by running optical fibers directly to your home, directly to the residences, faster internet access can be provided at rates on the order of 10 to 100 Mbps. This I'm talking about only 4G, so it's not 5G. So this design is called the FTTH, fiber to the home, and for business in commercial areas, it may make sense to lease a high speed transmission line from the offices to the nearest ISP, internet service provider. For example, in India, a T3 line, T capital T3 line runs at roughly 45 Mbps. That's what these were old data. So as now 5G is rolling out, now the things will change a lot. Okay, so that's how from cable, DSL, dial-up fiber, we have seen different types of speeds and different types of networks and various ways of connecting an internet to your laptop or to your home. So now let us look into cellular technology. What is a cellular technology? So a wireless way of connecting to the network is called cellular technology. So wireless is used for internet access too. So the latest technology, 5G mobile phone networks. So they can provide data delivery rates at almost 1 Gbps or higher to mobile phones and fixed subscribers in the coverage area. Thanks to the our honorable Prime Minister Modi for rolling out the 5G and is planning to completely roll out the 5G by end of this year. So we are fortunate to have this much of fast faced technological development, and we are fortunate to witness these kind of fast faced technological developments in India. So I thank him from bottom of my heart. So now let's get back to the topic again. So um, the present and existing technology is 4G. So 4G mobile phone networks can provide data delivery at rates up to 200 Mbps. Normally we maximum get at 100 Mbps, but it can provide up to, the hardware is designed in such a way that it can take up to 200 Mbps speed to mobile phones and fixed subscribers in the coverage area. The old technology was 3G mobile networks, and they can provide data delivery rates. They can provide data deliveries at a rate of 1 Mbps, and one the 3G is maximum 1 Mbps and or a little higher to mobile phones and fixed subscribers in this coverage area. So these are, before that we'll have a 2G, and then before that 1G, but they're not for the data transmission. They are just like digital calls and just for voice transmission. That's it. So 5G is 1 Gbps and more, 4G up to 200 Mbps, and 3G up to 100 MB, sorry 1 Mbps. Okay, these are the different types of generations of network cellular technology that has been developed in India, and as per the Indian government, they'll be starting to work on 6G technology by end of this year. And again, one more time, I thank this present Indian government from my bottom of my heart. So now let's look into ISP network. So we can now move packets between the home and the ISP. So we call the location at which customer packets enter the ISP network for service. The ISPs, it is known as point of presence, that you can see here. Here it is, point of presence, POP. So we will next discuss how packets are moved between point of presence to of different ISPs. From this point on, the system is fully digital and packet switched. So ISP networks may be regional, national, or international in scope. So we have already seen that their architecture is made up of long distance transmission lines that interconnect routers at POP, that point of presence, in the different cities that the ISPs serve. So this equipment is called the backbone of the ISP. Just at the beginning of this slide, we have seen that what is backbone, what is router, and what is subnet. So if a packet is destined for a host served directly by the ISP, that the packet is routed over the backbone and delivered to the host. Otherwise, it must be handed over to the another ISP. So now let us look into one more concept in this, that's called Internet Exchange Points, IXPs. Here you can see I have gave a brief about ISP before, but now let me explain little bit in depth. So after that we can go for the certain examples of how the data reaches to you. So for Internet Exchange Points, IXPs, ISP, that internet service providers connect their networks to exchange traffic at IXPs, internet exchange points. The connected ISPs are said to peer with each other. There, if you see this example in this slide, this is America's subnet, this is another network. So these two networks are connected through IXP. So basically what this process is called peering at IXP, because one network is basically peering into another network. So that's what we call it. Now here these are drawn vertically because the ISP networks overlap geographically. So basically an IXP is nothing but, you don't think it is something magical. It is just a room full of routers, at least one per ISP. So when I represented appearing at IXP with the dotted lines, you don't think it's something, some magical thing is happening here. Nothing. You will have a specific room to that, and we call that as IXP room, and then that's where the backbone of the America subnet and then backbone of the European subnets come, and they will connect it to the common router. That's what we call it as IXP, because that's where these two networks are being peer to each other. So that's what is called as a IXP, internet exchange point. That room itself is called as a IXP. So in this room, a LAN in the room connects all the routers. So packets can be forwarded from any ISP backbone to the any other ISP backbone. It could be regional, or it could be local, or it could be anything. From regional America's backbone to the European backbone, America's backbone to the Chinese backbone, Chinese backbone to the India's backbone. So IXPs can be large and independently owned facilities. So one of the largest is the Amsterdam Internet Exchange Point. You just Google it, Amsterdam Internet Exchange Point. So you will get it the complete information about that. Basically at Amsterdam Internet Exchange Point, hundreds of ISPs connect, and through which they exchange hundreds of gigabits, not gigabytes of gigabytes per second for traffic. That much of traffic will be there at the Amsterdam Internet Exchange Point, the one of the busiest internet exchange point is the Amsterdam Internet Exchange Point. Just Google it and do a bit of more research on that. Then we will look into a relationship between ISPs, how the ISPs can be can connect, and on what basis, whether it is financial basis or monetary basis or mutual understanding. So on what basis one backbone from the America and other backbone from the Europe can be connected. So that's what we are going to look now, because that is also very important aspect. So the peering that happens at IXPs depend on the business relationships between ISPs, internet service providers. For example, a small ISP might pay a larger ISP for the internet connectivity to reach distant hosts, much as a customer purchases a service from an internet provider. So, in this case, a small ISP is set to pay for transit. It's a proper way of putting this is pay for transit. Alternatively, two large ISPs might decide to exchange traffic so that each ISP can deliver some traffic to other ISPs without having to pay for transit. So, one of the many paradoxes of internet is that ISPs who publicly compete with one another for customers often privately cooperate to do peering, because without the coordination and without the cooperation it's very difficult to create a complete network across the globe. As I just said, one of the many paradoxes of internet is that ISPs who publicly compete with one another for customers often privately cooperate to do peering, because that's very important, or else it's very difficult to connect with another backbone in another region, or so that's very difficult. So the cooperation is very much required between different ISPs. Either you can pay for transit, or you can have a mutual cooperation and understanding without financial terms. So then let's then after that the path the path a packet takes through the internet depends on the peering choices of the ISPs. If the ISP is delivering a packet peers with the destination ISP, it might deliver the packet directly to its peer. Otherwise, it might route the packet to the nearest place at which it connects to a paid transit provider, so that the provider can deliver the packet. So, two example paths across ISPs are drawn in the above slide. Often, the path a packet takes will not be the shortest path through the internet. So it can take a longest path, or it can take a shortest path. So if data should be sent from America's backbone to the China's, either it can take this peering point or this peering points. Anyone it can take. So now let us look into the one more concept called uh, Tier 1 ISPs, Tier 1 Internet Service Providers. At the top of the food chain are a small handful companies like AT&T, AT&T, and Sprint. 33 operate large international backbone networks with thousands of routers connected by very high bandwidth fiber optic links. These ISPs do not pay for transit. They are usually called Tier 1 ISPs and are said to form backbone of the internet, since everyone else must connect to them to be able to reach to the entire internet or entire globe or entire world. So now let us look into the most important concept in getting a data from somewhere. Basically, now we are after we have gone through the each and every component of internet architecture, and now we are going to look into how does the data reach you. But to uh, to understand the data, to understand the principle behind the data reaching you, you must understand one important concept that is called data centers. Companies that provide lots of content such as YouTube, WordPress, Ghana, Netflix, Google, and Yahoo locate their computers in data centers that are well connected to the rest of the internet. These data centers are designed for computers, not humans, and may be filled with rack upon rack, rack upon rack, rack upon rack of machines called a server farm, like agricultural farm, a server farm. So, co-location or hosting data centers let customers put equipment such as servers at ISP POPs, at ISP presence of points, so that short, fast connections can be made between the servers and ISP backbones. So the internet hosting industry has become increasingly virtualized, so that it is now common to rent a virtual machine that is run on a server farm instead of installing a physical computer. So these data centers are so large, tens or hundreds of thousands of machines that these data centers consists of, and these data centers are large, that electricity is a major cost. So data centers are sometimes built in areas where electricity is cheap and where the climate temperature doesn't go too high, and where the temperatures are a bit of low, so that the cooling expenses for your system is also lesser. So now let's move on to, so we have, by and large, we have seen all the concepts that are related to the internet architecture. Now it's time to take a few examples to understand how does the data reach you, how data reaches you. So this ends our quick tour of the internet. Now we will discuss two examples that demonstrates how data flows from a data center to your YouTube on your mobile and laptop, and how each mobile phone communicates with each other. So presently you might be watching my video in YouTube either from your mobile or from your laptop. So that's why I've taken two examples how my video reaches you, either from mobile, either in mobile or laptop. So one one point I just want to put forward, and worth mentioning here, is that what it means to be on the internet is changing. It used to be that a machine was on the internet if it ran the TCP or IP protocol stack and had an IP address and could send IP packets to all other machines on the internet. However, ISPs, Internet Service Providers, often reuse IP addresses depending on which computers are in use at that moment, and home networks often share one IP address between multiple computers. So this practice undermines the second condition. So security measures such as firewalls can also partly block computers from receiving packets, undermining the third condition. So despite these difficulties, it makes sense to regard such machines as being on the internet while they are connected to their ISPs. So also worth mentioning in passing is that some companies have interconnected all their existing internal networks, often using the same technology as the internet. So these intranets, basically, if they are interconnected in the internal networks, these are called intranet networks, are typically accessible only on company premises or from company notebooks, but otherwise work the same way as the internetwork. So first, let us look into an example where a YouTube video from data center till reaches you at your laptop, which is connected through fiber. So here the end point, here the end data transmission or last leg or last mile data transmission is FTTH. That is this fiber to the home. Okay, let's see this example. So my video has been hosted in a server which is located in um, which is located in Silicon Valley of United States of America. So from there, when you request, when a guy from who's sitting in Europe, he requests for a video, my YouTube channel, then that from the server it passes through in bits, and then after the bits will be converted into the light signal, analog signal. So the digital signal will be converted into analog signal, and it will enter into the router, because this is also optic fiber, and then from the router it goes to the another line. It could be a backbone, and then from there it will enter into the at the peering point. Through the peering point it will enter into the subnet of the America of any tier 1 ISP, tier 1 internet service provider. From there there will be one more peering point, one more IXP, internet exchange point, and then through that internet exchange point, a room router, it will enter into the subnet of Europe, and then from there it will go to the backbone. From that backbone to the nearest router to your home, and from there through the optic fiber it will directly come to your laptop, because as it is connected to the optic fiber, it will directly come through the optic fiber and it will enter into your laptop. And from there you can able to see the video that I have hosted in in a server which is located in Silicon Valley of United States of America. So this is the first example. So now let us look into a second example. In the second example, where same YouTube video is hosted in a data center which is located in Silicon Valley of America, and then so that should go to the one who's residing in China, and who wants to watch that in mobile phone. So it's like YouTube video streaming from data center till YouTube on a Chinese personal mobile phone which is connected through the cellular network. This is the second case. Let's see how it works. So YouTube video is converted into analog signal, a light signal through the optic fiber. It has entered into the nearest router, and from the router into the backbone, and then into the subnet. From the subnet it will find a path. It will find the best path. We cannot say shortest path. It will find a path, and then it will find the IXP, internet exchange point, with the Chinese subnet or Chinese network, and then through that internet exchange point it will enter into the Chinese subnet, and then from the Chinese subnet router it will go into the backbone of the Chinese subnet, and then from the nearest router through the optic fiber cable it will find nearest antenna. So sorry, nearest cell tower, nearest cell tower, and then the cell tower consists of a transmitter, and that transmitter will base that transmitter will uh, once it reaches to the cell tower consists of a transmitter, and that transmitter will emit network signal. Basically, these are radio waves, electromagnetic radiation or electromagnetic waves, and these waves will propagate inside the propagate around, and then it will find out the receiver. It will find out the network, basically based on which operator, based on the sim card operator, based on the sim card operator and sim card operator location. It will directly go to that mobile phone. That mobile phone will have a receiver, and then that receives, and that guy will able to watch my video in his mobile phone YouTube application. So far, we have seen internet architecture and how uh, the data that reaches to you from the server till your home, and networking, and many other concepts of networking in depth. So now I would like to demonstrate all these concepts in a practical way. So in practical way doesn't mean I will create all subnet. I will set up a router, and then I will set up a network. No, not like that. So Amazon Web Services is the one I'm going to take as an example. In that, how they have used all these concepts and put together, they have created a web of services. They have created a cloud services so that everybody can access it. So now let's directly jump right into the Amazon Web Services. So this is the Amazon Web Services home page. So from here I will go to the VPC, that's Virtual Private Cloud Service. So here we can find all the concepts that were stitched together to make this virtual private cloud possible. So here you have all your VPCs. Now first let's begin with the subnet. Okay, subnet. So which region we are in? Mumbai region, that is in that is in India, Bharat. So in Bharat Mumbai region we have three subnets. So let me click one of the subnet. And but what is a subnet? The term subnet makes the most sense in the context of a wide area network. Of course, it is related to the wide area network only. So what is a subnet? A subnet refers to the collection of routers and communication lines owned by the network operator. So here Amazon Web Services has their own subnet. In Mumbai, they have three. For the Mumbai region itself, they have three subnets. Here, three subnets means their routers. Sorry, their routers and transmission lines, communication lines has been subdivided into three subnets. Out of which we will select this first subnet. In this subnet, that subnet area consists of a subnet ID, and this is the subnet ARN which we use in Kubernetes. And then this is version 4 CIDR. What is CIDR? So we will look into that during when we talk about the internet protocol versions and subnet masking. Okay, so that time I will say, but in the simplest way of telling is this subnet can have IP address of version 4 from 172.31.32.0 till 172.31.32. Exactly I cannot say how many, but these 32 and 0 can be varied. These 32 and these two last two octets, these two octets can be varied. So based on that you can calculate a lot of amount of lot of number of addresses we can get it for subnet, but 172.31 is common for this all IP addresses of this subnet, and 32.0 can be varied till 255. You can go till 255. Here 0 to 255 you can go, here from 32 to 255 you can go. So like that you can have a lot of combination. Here you can have 33 255, or 255 33, or 144 255. So a lot of combinations you can have here. So that's what CIDR do. And then see here they have mentioned available uh, IP version for addresses are 4091, 4091. So that was decided by this 20. Okay, this 20, what does it say? It is called subnet masking. We are going to discuss about this subnet masking in our forthcoming slides. And then this is the availability zone and availability zone ID. So route table, what is a route table? We are going to look into that. And this is the virtual private cloud name. So this is all about a subnet, and this is how subnet works, and this is how a subnet looks. So now let us move towards a route table, because there we have seen a route table. So let's move to the route table directly. So what is a route table, or a routing table? A routing table is a set of rules often viewed in table format. So that is used to determine the best route to enter into the other address. So before understanding the rules of the route table, let's see what is a router first. What is a route and a router? A router is a device that acts as a gateway to a network, and also is responsible for forwarding packets or messages to destination addresses. In addition, a router determines the best routes for forwarding packets based on the information stored in the routing table. So now let's look into the routing table. So based on this understanding of the router. Okay. So a routing table is a table, or in best way, in if you put it in a proper way, it's a database. It's a database that stores the location of routers based on their IP addresses. So this table acts as an address map to various networks, and is usually stored in the RAM of most routers or forwarding devices. As such, a routing table contains information about various networks and how to get to them, how to reach them, how to access them, how to catch them. So that is our routing table. For example, here we have one route table ID. So let's click on this route table and we'll see. This is the route table ID, and of course we cannot get it exactly that route table, but you can see these are the subnet association. These are the three subnet. This route table got associated with this ID, and then edge association, I don't think it's there. Route propagation, fine, that's it. Subnet association is very important, because the route table should be associated with certain subnets. So based on that, when data comes from the other network, that will be routed to this route table based on this subnet, and whatever missions, host missions that are presented in this subnet can be accessed through these route tables. So then from here, let's move towards um, uh, internet gateways. You can see this internet gateways. So what is internet gateway? A gateway or internet gateway is a device that routes traffic between networks. It is an intermediary piece of component that routes the traffic between different networks. It's intermediate between different networks. For example, at home, your router is your gateway. it provides a gateway between LAN, that's a local area network, and WAN, that's wide area network. So that's what is called internet gateway. If you want to explore more, you can just uh, here we have internet gateway ID. You can just click on the internet gateway ID, then we'll get a little bit of more information. But of course, this internet gateway ID, it belongs to this virtual private cloud, and this VPC belongs to Mumbai region, and this Mumbai region has 3 subnets. Okay, so then from here let's move on to egress only internet gateway. So what does egress only internet gateway? So an egress only internet gateway is a horizontally scaled, redundant, and highly available virtual private cloud component that allows outbound communication over Internet Protocol version 6 from instances in your VPC to the internet, and prevents the internet from initiating an IP version 6 connection with your instances. So that is all about egress only internet gateways. This is little advanced concept. You don't need to understand a lot at this moment, but if you want to create this service in AWS, you can just click on create egress only internet gateway, and then you can proceed forward. So now for this moment, let us move on to DHCP option sets. A DHCP option set is a group of network configurations used by EC2 instances. These are the virtual machines in AWS, Amazon Web Services, in your virtual private cloud to communicate over your virtual network. So each virtual private cloud in a region uses the same default DHCP option set basically to option set, unless you choose to create a custom DHCP option set, or if you dissociate all option sets from your VPC. So then what is, just a minute, yeah, what is DHCP abbreviation? It's Dynamic Host Configuration Protocol. That's what DHCP is. DHCP is Dynamic Host Configuration Protocol. So this is our DHCP option set. This is by default. If you want to create, you can create your own DHCP option set here. So let me look into the details first. Nothing much. The option set ID, and then domain name and the owner. So let me click on DOPT, and you can just access what is there. It's all about the same information. Okay, so now let's move on to elastic IPs. What is an elastic IP? An elastic IP An elastic IP address is a reserved public IP address that you can assign to any EC2 instance in a particular region until you choose to release it. So to allocate an elastic IP address to your account in a particular region, see, so basically normally what happens when you create an EC2 instance. Okay, let me just demonstrate this here. So let me copy this link and put it in yeah, once let me try to demonstrate this. Let me go to the EC2 instances service. Yeah, here it is. I'm in Mumbai region, so let me launch an EC2 instance in Mumbai region. Name, I'll just give Ubuntu. It's nothing special. So let me take Ubuntu and then 20.04 LTS. Then rest all remains same. I don't want to touch anything because it's just a sample. So I just want to proceed without key pair. Launch the instance. I want it as quick as possible. So then let me get back to the instance, and then here is the old instance. So this is the new instance, hasn't started, but you can see here this is the public IP. So basically auto assigned public IP. Okay, so now what happens, this public IP if I just a minute, let me get back to this. Yeah, it's running. This is public IP. Just remember 15206.291. Let me copy this. Let me take the sticky note. Sticky note. Okay. Let me close this and let me paste it. This is one and public IP. Yeah, got copied. Yeah, this is our public IP. So now let me get back to the instance. Let me go to the instance state. Let me stop it. Let me stop the instance, and then once it's stopped completely, we will restart the instance and we will see what is the public IP, because that's auto assigned public IP. So let's stop it. Once it is completely stopped, then we will uh, restart the Ubuntu server, and then we'll check the public IP. So then we can discuss about what is elastic IP based on this. So normally why I'm doing this is to demonstrate the first thing about the auto assignment of the public IP, and then elastic public IP. So this is stopped completely. So if you click on this, this was the previous public IP. So let me get back, let me refresh it. So nothing is there. So public IP was gone, the auto assigned public IP was gone. So because the machine was stopped, only you have a private IP address that would be remain same for it. So now what I will do is I will get back to the instances again, and I'll restart this instance, and we will see what's going to happen. So it's pending, instance state is pending. So let's wait for a few more seconds. Once the server is up and running, let's check the auto assigned public IP or just public IP and see what is going to happen or what is gonna happen. Still it's on pending. I think we require few more seconds, nothing much. So let's wait for the few more seconds. Yes, it's done. It's all up and running. Let me click on this. Now the public IP is this. So let me go back to the sticky note and paste it. Okay. This is the latest public IP, and this is the world public IP. So whenever you start or restart or reboot the server, the public IP changes, because this is auto assign public IP. So if you, after deploying any application in any server of your machine, of your in an EC2 instance in AWS, if the public IP changes, then how can you attach a domain to that? How can you attach a domain to that? How can you give this IP to somebody to access this application? It's difficult. So that is the reason, as these public IPs are auto assigned and they are not permanent, they will change every time the system got restarted and rebooted. So that is the reason we need an elastic IP. So what is elastic IP? An elastic IP is a reserved public IP address that you can assign to any EC2 instance in a particular region until you choose to release it. So to allocate an elastic IP address to your account in a particular region, just go to the elastic IP service in that VPC of in particular region. Now I'm in Mumbai, I just want to allocate elastic IP in this region. So now I will click on allocate public IP, sorry, elastic IP. Then so it will ask for the network border, so where I can give AP South 1 because it's in Mumbai. Then Amazon pool of IPv4 addresses and go for the global static IP address. Then you click on this create accelerator, it will create, and then finally if you want to add, you can add tag and then click allocate. That will allocate the elastic IP, and then you can use this elastic IP for your EC2 instance, and then after that you can deploy your application in that instance, and then that instance can be given to anybody. The IP of that instance can be given to anybody so that they can uh, access your application that you have deployed. This is all about elastic IP. We have taken enough time for elastic IP. Let's move to the endpoints. So endpoint, what is endpoint? An endpoint is the URL of the entry point for an AWS web service. The AWS software development kits and AWS command line interface CLI automatically use the default endpoint for each service in the AWS region, but you can specify an alternative endpoint for your API requests also. Endpoints are like many of the people knows about the endpoints, so I don't need to explain much about the endpoints. If you want to create an endpoint and if you want to add any service there, you can give endpoint name, and then whether you want to use AWS services, click here, or whatever you want to do, you can use it, and here you can select the services that you want to have. See, uh, there you give the endpoint name. If you want notebook and then airflow, uh, it's all up to you. Anything you can make it and then create the endpoint. This is how we use endpoints, and we get the benefit out of the endpoints. A web service endpoint is an entity, processor, a resource that can be referenced and to which web services messages can be addressed. This is one example. And endpoint references convey the information needed to address a web service endpoint. So clients need to know this information before they can access a service. So if you want to create an endpoint service, this is the way you have to name it: my endpoint, and then service name, and then version 1. So either network endpoint, basically if you want to use the load balancer, the load balancer should act like a network load balancer or just like a gateway. So depends upon that you have to mention, and then finally supported IP type, and then create. So now let's look into NAT gateways. What is NAT? NAT abbreviation is Network Address Translation. Network Address Translation. A NAT gateway is a network address translation service. You can use a NAT gateway so that instances in a private subnet can connect to services outside your VPC, but external services cannot initiate a connection with those instances. So that's what is called a NAT gateway. If you want to create your own NAT gateway, this is the way. You have to click on create NAT gateways, and you can create your own NAT gateways. And then finally we have a peering connection. Peering connection that we have used a lot in our explanation. So what is peering connection? Now you can see practically a peering connection. For example, here in this case we are in Mumbai region, and we are in the virtual private cloud of Mumbai region, and this VPC consists of 3 subnets. So a VPC peering connection is a networking connection between 2 VPCs that enables you to route traffic between them using private IP version 4 address or private internet protocol version 6 addresses. Instances in either VPC can communicate with each other as if they are within the same network. If I want to put it very simply, so let me get back. As you have seen all the terminology of virtual private cloud practically, so now let me get back to the instances global view, EC2. Okay, I would find EC2 instance here only. So here it's EC2 global view. Let me click on this EC2 global view. So once we reach there, I'll show you something magical. Yep. So here, how many we have a lot of regions. For example, in Asia Pacific, Hyderabad is one region. Okay, we'll take Mumbai region. Mumbai has three subnets and one private VPC. And then we have Canada. Canada has one VPC and three subnets. So now, for example, I have opened and I have created an EC2 instance in Mumbai region here in this private cloud. And then there is one more EC2 instance in Canada in this private cloud VPC. So now if this one has to communicate with this, means how it is possible? This is only possible through the VPC peering connection, through VPC peering connection, virtual private cloud peering connection. That's what the peering connection I'm talking about, and this is how it works. So now let's look into addressing and subnetting. So there are two types of addressing. Basically, the first way of doing is hardware addressing. Hardware addressing is a hardware address is used to uniquely identify a host within a local network. So hardware addressing is a function of the data link layer of the OSI model, that is layer 2. Data link layer is OSI, data link layer is layer 2 in OSI model. Then it uses Ethernet. Ethernet utilizes the 48-bit MAC address, that's a MAC address, as its hardware address. So MAC is nothing but media access control address. MAC address is media access control address, is often hard coded on physical network interfaces, though some interfaces support changing the MAC address using special utilities. In virtualization environments, dynamically assigning MAC address is very common. So a MAC address is most often represented in hexadecimal using one of two accepted formats. Here you can see those two formats. Um, these are two examples, but I would like to show this in live. So just a minute, I would like to put the yes. So this is the Wi-Fi. So my wireless network is example. I'm checking this as my wireless network. If you see physical address here, the physical address MAC is 74 4C A1 78 98 D1. So basically IP4 and DNS server encrypted IP6, and then the link speed is 150 Mbps and network band is 2.4 gigahertz. These are other information, and the version, if you see, the standard is 802.11n that we have discussed at that time. So here is the example. So like this, every maybe your mobile phone will have a MAC address. Your mobile phone Bluetooth is the example that will have a MAC address. So everything, almost each and every device will have this physical address, and how much we are using, that's debatable, but uh, every device will have a physical address. The first, in this address, total we have six hexadecimal digits. Total we have six hexadecimal digits. In this, the first six hexadecimal digits of a MAC address is identified as if you see this, the top one total we have 2 plus 2 plus 2 plus 2 plus 2 plus 2, total we have uh, 6 plus 6 12 hexadecimal digits, out of which the first three components, initially I said the 6 hexadecimal digit, na? So the mistake is, it's not 6 hexadecimal digits, 6 hexa, total six components it consists of. Total six components. There's a two formats. The first format will have a six components, and second one will have three components. Out of the six components, let's consider these first three components, or the first six hexadecimal digits of this MAC address identify the manufacturer of the physical network interface. Basically, this is referred to as the OUI, that is Organizational Unique Identifier. Then we have the last three components, or the last 6 digits uniquely identify the host itself and are referred to as the host ID. These three are the host ID. So the MAC address has one shortcoming. What is that? It contains no hierarchy. So MAC addresses provide no mechanism to create boundaries between networks. So this is not one shortcoming. This is the biggest shortcoming of the MAC address or the physical address. There is no method to distinguish one network from another, because these are individual, directly, specifically addressing a device. It's a physical physical addressing physical addressing. So this lack of hierarchy poses a significant difficulties to network scalability. if one if only layer 2 hardware addressing existed, all hosts would technically exist on the uh, same network. So internetworks like the internet could not exist, as it would be impossible to separate my network from your network, and your network from my network, and my network from others network, because there is no way of separating. So imagine if the entire internet existed purely as a single layer 2 switch network. Switches, as a rule, will forward a broadcast out every port. With billions of hosts on the internet, the resulting broadcast storms would be devastating, and the internet would simply collapse. So the scalability is the biggest limitations of layer 2 hardware addresses are mitigated using logical addresses. So let us see logical address. So logical addressing is a function of the network layer of the OSI model. So that is layer 3, and provides a hierarchical structure to separate networks. So logical addresses are never hard coded, never ever, never ever hard coded on physical network interfaces, and can be dynamically assigned and charged freely. So a logical address contains two components. First one is a network ID, which identifies which network a host belongs to. That's where my network, your network, and other network can be distinguished. So, and the second part is host ID. Host ID is nothing but uniquely identifies the host on that network. So examples of logical addressing protocols include the Internet Packet Exchange IPX. This is one protocol, and then Internet Protocol IP, and then but IPX, Internet Packet Exchange, was predominantly used on novel networks, but is now almost entirely deprecated because of IP. So IP is the most widely used logical address, and is the backbone protocol of the internet. So now let's look into Internet Protocol, IP. Internet Protocol. So in the 1970s, the Department of Defense developed the Transmission Control Protocol, TCP, to provide both network and transport layer functions. When this when this is proved to be an inflexible solution, those functions were separated, with the Internet Protocol providing network layer services and TCP providing transport layer services. Together, TCP and IP, that the transport control protocol and internet protocol, provide the core functionality for the TCP/IP. Or now let us dig deep into the Internet protocol and Internet protocol version 4 addressing and subnet masking and these kind of things. So let's look into the some basic concepts before taking up Internet protocol version 4 and then subnetting or subnet mask. So Internet protocol IP. So IP provides two fundamental network layer services. First one is logical addressing. Logical addressing provides a unique address that identifies both the host and the network that host exists in. And routing. Routing determines the best path to a particular destination network and then routes data accordingly. Then IP version 4. IP version 4 or Internet Protocol version 4 was the first version to experience widespread deployment and is defined in RFC 791. So Internet Protocol version 4 employs a 32-bit address. It's a 32-bit address. It consists of 32 bits. So which limits the number of possible addresses to only 4294967 So this much only you can have. You cannot have more than that. Okay, so IP version 4 will eventually be replaced by IP version 6 due to a shortage of available IP version 4 addresses because IP version 4 can only have this much, only this 4294967 only this much of addresses it can provide. So that is the reason eventually we have to replace IP version 4 with IP version 6. So now let's look into IP version 4 addressing, but it will take a lot of time. So IP version 4 addressing, a core function of IP is to provide logical addressing for hosts. An IP address provides a hierarchical structure to both uniquely identify a host and what network the host exists on. An IP address is most often represented in decimal format. You can see the format on your screen. So that is one example is 158.80.164.3 and I will show it, I will demonstrate it practically also. So let me come, this is EC2 global view. So let me get into EC2 service, anything, EC2 service. Just we can use anyone. So I'll go to the instances in Mumbai. So we have one instance that's running. You can see this. So example is this. Public IP is 65.279.11 dot, and then private IP is 172.31.6.243. So we have what is public IP and what is private IP. That's not very important for this moment. So now just look into how IP looks, the version 4. So version 6 is different completely, but how a version 4 IP looks like, you got it, 65.279.11. So here example we have taken is 158.80.164.3. so in this we have 4 octets. So each octet is an 8-bit number resulting in a 32-bit IP address. the smallest possible value of an octet is 0. A single octet, any single octet can have the smallest possible value of a 0. Like when each octet consists of 8 digits, so if all 8 digits are zeros, then obviously the value would be 0. And the largest possible value of an octet is 255. If all 8 digits are ones, then the largest would be 255, 255. So in binary it's at all ones. So 0 to 255, this is the maximum possible values, minimum and maximum possible value of each octet. So based on this, because of this zeros and 255, so with that permutations and combination, we come up with this value 4294967 Now the above IP address is represented in binary. If you see this one, um, here this is first octet 158, second octet 80, and then third octet is 164, and then fourth octet is 3. So this is how it looks, and it consists of 4 octets, and total it's a 32-bit. I will show you how it is 32-bit. This is in normal language, so that it's octal, it's octal. Now let us convert this into binary, and we'll see how does it look like. So each octet is an 8-bit number, so resulting in 32-bit IP address that you can see. First octet 1001110 158, and second octet is 0101 4 zeros. That's how you can convert a octal into binary digits. And the third octet and then fourth octet, if you count total how many bits, let me count it. 1 first bit, second bit, third bit, it has become 8-bit, and this is 8 bits, and this is 8-bit. 8 plus 8 plus 16 plus 8 24, 24 plus 8 bits, that is uh, 30 32. Yep. So total we got a 32-bit IP address. So this is how IP version 4 looks like. So now let's look into the subnet mask. Subnet mask. When I say the subnet mask, you might be confused with the subnet. No, not at all. Never ever get confused with the subnet and then subnet mask. The subnet is the hardware concept, and the subnet mask is the software concept. So what is the subnet? Subnet is the collection of routers and communication lines. That's it. That is your subnet. Whereas a subnet mask is completely a different concept. It's related to the IP addressing. It's related to the internet protocol. It's not at all related to the hardware concept. So this is called the subnet mask, and that is subnet. So the subnet mask is part of an IP address, so which identifies the network. So the other part of the address identifies the host. So if you see this total IP version 4 address, out of which one part will identify the network, other part will identify the host. So a subnet mask is required to provide this distinction. So now you got the difference. What's the difference between a subnet and then subnet mask? A subnet is a hardware thing. It's a collection of communication lines and then routers which are specific to one region. And then subnet mask is the one which makes the distinction between which part of IPv4 address is host and which part of IPv4 address is network. So the above, let's take this example one. So this address has a subnet mask of 255.255.0.0. So what does it say is Normally the subnet mask has only two rules, just two rules. If binary is set to a 1, if binary is set to a 1, total we have 32 bit, right? We have 32 bits, right? In that, if binary is set to 1 in a subnet mask, the corresponding bit in the address identifies the network. If a binary bit is set to a 0 in a subnet mask, the corresponding bit in the address identifies the host. I think you are pretty much confused with this. Okay, don't worry, I'll just explain uh, on the slide also. So just take this example. So this is our address, this is our IP version 4 address, and then this is our subnet mask. That's clear. So if you look at this with octals, it's very difficult to understand the rules of subnet mask. What will we do now is we will convert this into binary form. So we'll convert this into the binary form. Looking IP address in binary form, this is how it looks. Total it has 4 octets. So ones, zeros, one zeros, total 32 bits. Now let's look into subnet mask. Ones, and then second part all ones, and then third octet all zeros, and then fourth octet all zeros. Now what does it mean? So what does it mean is, for example, if you take any bit, I am taking the first bit of the subnet mask. The first bit of the subnet mask is 1, and then, so what it says is, if this is 1, the corresponding bit of IP address represents network, if it is a 1. And what is the second bit? Second bit is also 1. So if the second bit also 1, the second bit, the corresponding second bit of the IP address represents a network. And then what is this third bit? Third bit is 1 in subnet. So the corresponding third bit of IP address represents 1. So now how many ones we have in this? So we have first octet all are ones, second octet all are ones. So what does it mean in? What does it mean is, the first 2 octets of the IP address represents network. This 2 belongs to network. So 15880, these 2 octets represent network. So now zeros has begun. So what does 0 means? 0 means if almost this one is 17th bit. 17th bit of subnet mask is 0. It does mean the corresponding 17th bit of IP address represents host. That's it. So now what all are 0 in subnet mask. Third octet and fourth octet all are 0. It means this second, the third and fourth octet of IP address represents host. They identifies host. So now to make it simple, so this one, the first 2 octets of IP address talks about the identifies the network. Once you enter inside the network, then this many combinations you can have to identify your hosts. That's it. Okay, this is one example. I will practically explain the same thing in forthcoming sessions. So just to explain one more time, the first 16 digits of subnet mask are set to 1. Thus the first 16 bits of address 158.80, the first 2 octets identifies the network, and then the last 16 bits of the subnet mask are set to 0. Thus the last 16 bits of the address, that is the third and fourth octet of the IPv4 address, that is 164.3, identify the unique host on the network. So the network portion of the subnet mask must be contiguous. For example, If you want to take 255.0.0.255, that is absolutely not valid. So this kind of thing is not valid. So first two should be at least 2 octets should be given for the network identification. So now let us some examples related to subnet masking. So first condition that we are going to consider is hosts on the same logic, same logical network will have identical network addresses and can communicate freely. For example, the following two hosts are on the same network. Host A is 158.80. These are the first two octets, and then 164.100. Okay, and then subnet mask that we have used is 255.255.0.0. This means the first two octets are identifies network, and second two octets identify obviously host. So and host B consists of 158.80, again with the same subnet mask, similar subnet mask. That means the first two are network and second two are host. So they are in the same network. By looking at the IP addresses, we can say that both are in the same network, but the host identification is different. One host A identification of last octet is 100, and host B last octet is 101. So both share the same network address, that is 158.80, which is determined by the 255.255.0.0 subnet mask. Because of that only we are able to make out which part identifies the network and which part identifies the host. So hosts that are on the different networks cannot communicate without an intermediating device. So now let's take another example where where we can have a different networks. Both are in different networks. So for that we have to look into the subnet mask only. So subnet mask is very important, very important. So now the second example that we have considered is the subnet mask. If you see, the subnet mask has remained the same here, but the network, if you see the following example, the subnet mask is 255.248.0.0, and then other subnet mask is 255.248.0.0. So first one is 255. That means the first octet will definitely represent what do you say, sorry, network. And then the second octet, how many digits, how many bits in second octet will represent a network, and how many bits in second octet will represent host, that we do not know. For that reason we need to look into the subnet mask. Sorry, for that reason we need to look into the we need to convert it into the binary form. So let's convert this into the binary form. So here is host A consists of this, that is IP address, and host B IP address, and the subnet mask is this. Okay, so as both has the same subnet mask. If you see first octet, the first 8 bits represent obviously network, but whereas in the second octet only 5 bits will represent network, and then last 3 bits of the second octet will represent your host. So now we have only 2 octets, that's it. So anyway, the last 2 octets obviously represent host. So now based on that, it's very pretty clear that host A and then host B. So you have to consider these first two, and out of which the first octet is same but the second octet is not same. Of course their host ID is same, but the network is not same. You see, 158.80 here, 158.79. So these are in different networks, but in their network but they have same host names, same host IDs. That's what here basically the two hosts are not on the same network and cannot communicate without a router between them. If they are in the same network, you do not require a router to communicate with each other. They can communicate with each other without any router. So that's how it works in the if you create instances that we will do in Kubernetes. In Kubernetes, if you create instances in same region, same subnet, same VPC, you don't need to have a router to communicate with each other. So there we create a Kubernetes cluster. I will show that. So don't skip the course after completing the networking. You just follow the whole course, because there is a lot of stuff ahead, lot of knowledge ahead, and a lot of practical workings and a lot of practical exercises ahead. Okay, so now normally the hosts which are not on the same network cannot communicate without a router between them. So that's why routing is the process. Routing is must and should for communicating two hosts which are in different networks. So routing, what is routing then? Routing is the process of forwarding packet from one network to other network. That's what is called a router. At your home you might have a router. So what does a router do? A router basically forwards a packet from wide area network to your local area network. That's it, nothing much. That's what is your router. So here you can see we got yeah, host A's network ID and host B's network ID. You can see they are not at all same. That's a clear cut explanation I have added here with the binary digits. Always, if you want to understand exactly the IP, you have to look into the binary. If you look into the binary, then only you will get exactly what's happening behind, or else it's difficult to figure it out. So 158 and 157, 158.80 and 150.7, and this is our network. If you look into the binary, so it's completely different. Okay, the first two octets are same, but the second octet, the five bits are not similar. So there is a difference. So that is the reason these are two different networks, and the host A is in different network, host B is in different network. So far we have seen uh, internet protocol and IP version 4 and subnet masking and everything. So now let us look into internet protocol address classes, IP address classes. The IP version 4 address space has been structured into several classes. The value of the first octet of an address determines the class of the network. So based on the first octet, the value of the first octet determines into which class it falls in. So we have four classes: class A, class B, class C, class C. Class D. So in class A, the first octet ranges from 1 to 127, and in class B, the first octet ranges from 128 to 129. In class C, the first octet range from 192 to 23. In class D, the first octet range from 224 to 239. So if you look into the default subnet mask in class A, the first octet is the only octet that identifies or defines the network. In class B, the first two octets identify or defines the network. In class C, first three octets defines the network, whereas in class D there is no specific default subnet mask. So now what will we do is deep let's deep dive into each class. Let's begin with class A. So class A network basically ranges from 1 to 127, as we have discussed earlier, and it has a default subnet mask which is 255.0.0.0. So what does it mean? So it means um, the first octet only defines the network, and the last three octets define the host. So basically I would urge you to also focus on the color scheming that I have put here. So red means actually the red defines the network, and then the black defines the host. If you see, if class A network, only the first octet the first octet defines network, and then remaining three black octets define only host. Okay, so because as it has only one octet to define network, so you have maximum of 127 class A networks, and it has three octets to define the network. So it has 1 crore 67,000 1 crore 67 lakh 77,214 hosts per network. And now let's move into class B network. As usual, as we have discussed earlier, class B network basically range from 128 to 191. So the default subnet mask it has is 255 dot 255.0.0. So what does it mean? It means the first two octets define the network, and the last two octets define the host. So based on this logic, this subnet mask results in a maximum of 16,384 class B networks with 65,534 hosts per network. And we have class C network. As we have discussed just a while ago, class C network ranges from 192 to 223, and it has the default subnet mask of 255.255.255.0. So as per our understanding, the first three octets define the network, and last octet basically defines the host. So this subnet mask results in a maximum of 2 crore 97,152 class C networks with 254 hosts per network. It's obvious that it has more number of octets, so that is the reason it more number of octets that define the network. So it has huge amount of networks, whereas coming to the hosts per network, it has only one octet to define the host. So we have just 254 hosts per second, but the total capability of this has, if you multiply your maximum uh, maximum number of networks it can have with the maximum number of hosts per network, you can get the total number of hosts that class C network can hold. And finally, we have Class D network. As usual, Class D networks are reserved for multicast traffic. So that is the reason, as we have discussed earlier, they do not use a subnet mask at all. They are basically reserved ones, and they are specific. So they don't need a Class D. They don't need a subnet mask. Now let's look into practical demonstration of CIDR, classes inter domain routing. So classless inter domain routing, so that demonstration, the CIDR demonstration we can see. So now we are in Amazon Web Services console. So in Mumbai region, with this private clouds, with this virtual private cloud. So in that, the Mumbai region has one subnet. I think total Mumbai region has three subnets, I guess. Let me check here. So this is in Mumbai region only. Let me okay, I'm in global view here. Yeah, here it's Mumbai region. It has I think These are, here we have subnet, only one subnet. Let me confirm once. Just confirm y2. Okay, AC2 global view. Yep, we are in AC2 global view. Here is Mumbai, and then only one VPC and three subnets. Yes, one VPC and it has three subnets. So here, out of three subnets, so let's click on these three subnets. So I think in which subnet we are, 7 9. So 7 9. So this is the subnet we are in this. So in this subnet we are in. So in that subnet, so if you look into the IPv4 CIDR. So this is what I just want to demonstrate. So whatever theory that we have seen, that's not enough. We should know where they use it exactly, so that then only there is some purpose, then only there is some use or need of teaching a theory. So that's the reason I would always like to demonstrate every concept in practically. So here you can see IPv4 CIDR. So for this subnet we have CIDR of this. Can anybody explain me what does this mean? Because we have gone through the CIDR and subnet mask. So I will only explain. So here we have 172.31.0.0. This is our IP version 4. That's a IP version 4. That's it. And after that we have CIDR, that is /20. So normally, so we have /20. That means 20 ones. So first 8s are ones. The first octet all are ones. Second octet all are ones. Total how many it has become? 8 plus 8 16. Then in third octet total 8 we have. Out of 8, 4 are ones. So total 16 plus 4 20. So that means the first octet and second octet and half of the third octet basically represent network, and then half of the third octet and then half of the and complete a fourth octet represent the host. So that's what we got it. Now the 1 2 3, by and large these three represent network, and of this third one and then complete fourth octet represents host. That's what this IPv4 CIDR says. Now based on this logic, now we can have plenty of permutations and combinations based on total this combination. So we can have 204090 available IP version 4 address. So you can have more, but at this moment we have only these many. Okay, so that's how you use IP version 4 CIDR. Similarly, you can have IP version 6 CIDR also. So now let's go into the virtual private cloud IP version for CIDR, and we'll see what is the difference between IP version for CIDR of virtual private cloud and then subnet. So now say Mumbai region. So as I have shown you, Mumbai region has three. Mumbai region has one virtual private cloud and then three subnets. So here if you see, it has one virtual private cloud and three subnets. So now let's go into the virtual private cloud, as it has only one. So now let's see what is that. And here you can see DHCP option set that we have discussed earlier. And here you can see maintain a route table. You have a route table also here. Okay, so now here you can see the IPv4 IP version 4 CIDR exactly at this. I have marked with the blue color. So, and what is this? it is 172.31.0.0 /16. IPv4 is just 172.31.0.0, whereas CIDR is /16. And for subnet it was 172.31.0.0. For subnet IP is same for virtual private cloud or subnet, because based on subnet only this IP will be given to the VPC. So IP is by and large it's same, whereas CIDR is /20 year, and CIDR is /16. So what does it mean? /16 here. So here the first octet comes up with 8 bits, and then second octet comes up with 8 1 bits. So total 8 plus 8 16 bits. This means the first octet and then second octet only represent network, and then remaining two octets represent host. So that means you can have a lot of here in this case you can have approximately around 60,000, approximately 60,000 host machines per network, and 16,000 networks. So as per this, but of course, so that's the total count, but here you can have only 172.31, only this piece. So in this you can have zero neglect, so you can calculate that also. 2 power n for the number of networks, and then so here 2 power n times 2, and then you can have 2 power n minus 2 to calculate the number of host machines per 2, because whatever calculations that I have given before, those are for the class B in totality. But here if you want to specifically calculate, because this network is fixed, network would be 172.31 only. So what else you have is only last two octets can be altered, can be changed. So here you can have the combinations and permutations, and you can do that calculation also. You just take out 0 and 1 for the host machine. Other than that, that's why we use 2 power n minus 2 to calculate the useful host machines that can be created per network, and then 2 power n are the networks that we can create. So in this, so as we have two octets, the number would be high. So that's how we use. So now you may get doubt, is it possible for us to create our own CIDR? Yes, of course it's possible. We have a specific service for that. That's called create CIDR collection. CIDR collection. So to create CIDR collection, you must create at least one CIDR location with CIDR block. So all record sets with the same record set name and type must reference the same collection. So you have to give some collection name. At least you should create one CIDR collection, and after that you can add. So that's the collection name you have to give, and then you have to add a location here. And then for example, this is how it looks. Okay, I have added two are not required, one is more than enough. CADR location, so location name, and then just example is given, list of IP addresses from 0 to 24. You can set up for IP version 4, you can have only from 0 to 24. If you put 0 or 8, or means it would be very less number of machines you can have for your network. If you go for the 24, you can have a more number of machines, host machines, usable host machines for your network. That is all depends upon your requirements, how many instances that you would like to have per your network. I hope the practical demonstration of CIDR is much clearer, and now overall, if you put all pieces together, it should make more sense for you. So far, we have discussed IP addressing and subnet mask, then alien concepts. So now I would like to take you through a brief explanation about netting, subnetting, and allied algorithms, and how does this work. So subnetting is the process of creating new networks by stealing bits from the host portion of a subnet mask. So there is one caveat: stealing bits from hosts creates more networks, but fewer hosts per network. So the best example is when we were looking at classes of IP addresses. At that time, we have seen class A, class B, class C, class D, three, almost four classes. Out of which, if you see the default, each has the default default subnet mask. So if you see, as you move from class A to class C, as you move up from one subnet mask to other subnet mask, the number of octets that define the uh, network has been increased. So because of that, the number of per hosts per network will reduce. So consider the following class C network. So class C network, as I have told you, it consists of three total four octets, out of which three octets define the network and one octet uh, define the host. So the default subnet mask for this network is 255.255.255.0. So this single network can be segmented or subnetted into multiple networks. For example, assume a minimum of 10 new networks are required. Resolving this is possible using the following magical formula, that is 2 power n. So the exponent n identifies the number of bits to steal from the host portion of the subnet mask. So the default class C mask, that is, it consists of the default class C mask. The subnet mask for the class C is 255 dot 255.255.0, which if we convert that into binary, it looks like this, absolutely looks like this: 255 all ones, 255 all ones, 255 all ones, 0 all zeros. So that's how it looks. Now there are a total of 24 bits set to 1 out of total 32 bits. 24 bits set to 1, which are used to identify the network. So there are a total of 8 bits set to 0, which are used to identify the host, and these host bits can be stolen. So stealing bits essentially involves changing host bits that was set to 0 in the subnet mask to network bits, that means setting to 1 or 0. So if you put it in a simple way, so you have total 24 ones and 8 zeros. What you can do is you can replace fewer bits from these zeros as 1. So this 0 can be converted as 1, so then automatically that will be converted, that bit will be converted as a network. As a network, the bit will be converted as the bit which represents or defines the network. So remember, network bits in a subnet mask must always be contiguous. Skipping bits is not allowed. So consider the result. If 3 bits are stolen from this, so this first 3 are stolen from this using the above formula, so 2 power n, so total we have stolen 3 bits. To cube, total 8 networks can be created. Absolutely correct, absolutely correct. So however, a total of 8 networks does not meet the original requirement of at least 10 networks. So consider the result if 4 bits were stolen. If you steal 4 bits, 1, 2, 3, 4, then 2 power 4 equals to 16. 16 networks created, or 16 networks can be created. So a total of 16 new networks does meet the original requirement. So stealing 4 host bits results in the following new subnet mask. After stealing, okay, you have stolen these four bits. That means these 4 zeros has to be replaced with ones. So that's what, after stealing 4 host bits, so results in the new subnet mask. It exactly looks like this. So now we have one more rule to do the similar kind of calculation, that is 2 power n minus 2 rule and subnetted networks. So what is this? So in the previous example, a class C network was subnetted to create 16 new networks using a subnet mask of 255.255.255.240 or 240. So basically, when you convert this into CIDR, it will become like the IP of that this thing, and then forward slash, this it will become a 28, because 8 plus 8 plus 8 plus 4, so 24 plus 4, 28. So 4 bits were stolen in the subnet mask, leaving only 4 bits for hosts. To determine the number of hosts, this results to determine the number of hosts, this results in, for each of new 16 networks, a slightly modified formula is required. For that, what we use is 2 power n minus 2. So let's do the calculation. 2 power n minus 2. So let's put how many, consider the result if 4 bits are available for the host. So 2 power n minus 2. So we have, how many bits are available for host? Only 4. 1, 2, 3, 4. So 2 power 4 minus 2. So 16 minus 2. So 14 usable hosts per network. We use 2 power n, basically 2 power n, to get the networks, how many new networks can be created, and 2 power n minus 2 to get the how many usable hosts can be created per network. So thus, a subsetting a class C network with a forward slash 28, that CIDR forward slash 28 mask, in spite of saying 255.255.255.240, you can simply put it as forward slash 28 mask. So creates a 16 new networks with a 14 usable hosts per network. So, but before we conclude this calculations, so why uh, why 2 power n minus 2 rule is used? Why is the formula for calculating usable hosts is 2 power n minus 2? Why not just 2 power n plus 2 or something? Because it is never possible to assign a host an address with all zeros or all one bits in the host portion of the address. So these are reserved for the subnet and broadcast addresses. We have seen in our previous slide about the broadcast address. If all are ones, then we call it as a broadcast address or subnet address. So broadcast or subnet address, so zeros and ones will be reserved for those purpose. So that is the reason always you minus 2 hosts from the formula. So thus every time, so 0 is for subnet. If all are zeros, that represents a subnet. If all are ones, that represents a broadcast address. So that's the reason every time a network is subnetted, usable host addresses are lost. So that's the reason our formula to calculate the number of usable hosts per network is 2 power n minus 2, whereas number of new networks that can be created is 2 power n. I hope you got it clear. You got it everything. And if you have any doubt, just ping me on comment section. So now I'm going to talk about a topic which is widely useful irrespective of what domain you are working. So that's about the difference between a public IP and a private IP. So let's begin with the public IP. So a public IP can be routed on the internet, thus hosts that must be internet accessible, must be configured with or rechargeable by. So public addresses, allocation of public addresses is governed by the internet assigned numbers of authority, that's IANA. And we have a private IP. So private IP is intended for internal use within a home or organization and can be freely used by anyone. However, private addresses can never be routed on the internet. In fact, internet routers are configured to immediately drop traffic with private addresses. Let's see some of the private addresses range that were defined. So there are three types of private address ranges were defined in RFC 1918, one for each IP version 4 class based on the IP version 4 classes. So let's begin with the class A. So class A address range begins with 10.10.0.0.0 to 10.255.255.255, whereas the class B address range begins with 172.16.0.0 to 172.31.255.255, and finally class C private address range begins with 192.168.0.0 to 192.168.255.255. So it is also possible to translate between the private and public addresses or private and public IPs using network address translation. So what it does, NAT allows a host configured with a private address to be stamped with a public address, thus allowing the host to communicate across the internet. It's also possible to translate multiple privately addressed hosts to a single public address, which conserves the public address space. So let me take you through the practical run. So then it would be much clearer. So here you can see it's related to the virtual private cloud. In this virtual private cloud, we have NAT gateways. So I have clicked on this NAT gateways. If you see the NAT gateways, at this moment there is no NAT gateways. What is a NAT gateway? A NAT gateway is the one which actually translate between private and public IPs. So NAT is network address translation. So let me create a NAT and see what's going to happen. If you use this service, you have to give the name and then subnet that you are using. So we have three subnets in Mumbai region. I will select any of the subnet and here I'll give my NAT gateway or my whatever it may be. So then what type of connectivity you want, whether it is public or private, you can go with the public so that everybody can access, and here you have to allocate elastic IP, and then finally you can add tags and you can create NAT gateways. This is how a NAT gateway works. Normally NAT provides an additional benefit. What is that? Hiding the specific addresses and addressing structure of the internal or private network. So NAT is only a temporary solution to address a shortage problem. So IP version 4 will eventually be replaced with IP version 6, which supports a vast address space. When that comes, you don't need to use this NAT anymore, because as we have discussed earlier, NAT has sorry IP version 4 has some limitation in giving the IP Internet Protocol addresses. So that is the reason to overcome this. We are using NAT, so Network Address Translation. So whereas once we completely move or switch over to IP version 6, IPv6, this problem will be solved, and we don't need to use anymore. We don't need to use NAT anymore. So that's the reason NAT is only a temporary solution. So now let's look into some of the reserved IP version 4 addresses. So the first one is the 0.0.0.0 forward slash 0 network is used to identify all networks. You can see mainly in AWS and those kind of Google cloud platform. So there you will find these kind of addresses. When you see this, what does it say is, it says it referred to the default route. That's it, nothing else. It referred to the default route. It identifies all networks. And there is one more type, that's 0.0.0.0 forward slash 8 range. Forward slash 8 means obviously the first octet only defines a network. So this range is used to identify hosts on the local network. That when you basically see on your laptop, when you try to host some application in your personal machine, or when you run a HTML file in your personal laptop. At that time, the local network, the local IP address would be like this. All are zeros and the forward slash 8. So then the third, the entire 127 x forward slash 8 range is reserved for diagnostic purposes. So the most commonly used address in this range is 127.0.0.1. Then the third one we have is the 169.254.x.x forward slash 16 range. So obviously the 16 is our CIDR. That means the first two octets they represent network, and last two octets represent hosts. So this range is reserved for automatic private IP addressing, that is APIPA, automatic private IP addressing. And the fifth one is the 224.x.x.x to 213 on the 239.x.x.x ranges are reserved for multicast and are referred to as class D addresses. We have seen that in classes the class D addresses are multicast. And the 240.x.x.x to 255.x.x.x ranges are reserved for future and experimental use, and were formerly referred to as class E addresses because they are not allowed to use, they are only for the future and experimental use. And the final one, the 255.255.255 address can be used as a broadcast address for the local network. So now let us dive into these concepts more. So let's understand how one host machine communicates with another host machine if they are in same network, and similarly how one host machine communicates with the other host machine if they are in a different networks. So to understand that, let us look into the following concepts one by one. So for the first one is resolving logical addresses to hardware addresses. Say a host cannot directly send data to another host's logical address. A destination logical address must be mapped to a hardware address so that the data link layer can package a frame to transmit on the physical medium. So The Address Resolution Protocol, ARP, capital A, capital R, capital P. The Address Resolution Protocol provides this mechanism for Internet Protocol version 4 on Ethernet networks. So ARP, Address Resolution Protocol, allows a host to determine the MAC address for a particular destination IP address. So let's consider the, uh, the diagram which is shown on the screen. So this demonstrates the steps required for host A to communicate with host B if they are in same network. First, let's begin with host A. So host A is our machine which is on the left side, and host A will determine if the destination IP address of 10.1.1.6 is itself. So if that address is configured on a local interface, so the packet never leaves host A. So in this example, 10.1.1.6 is not locally configured on host A. So next, host A will determine if the 10.1.1.6 address is on the same network or subnet as itself. So host A consults its local routing table to make the determination, to make this confirmation and determination. In this example, the subnet mask is 16. You can see the subnet mask, that CIDR, is /16. Thus host A's IP address of 10.1.1.5 and the destination address of 10.1.1.6 are on the same network, that is 10.10.1. So that is the common network both are in. So this is host A and this one is host B, and both are in the same network because mm, based on our subnet mask or CIDR. Okay, so now because host A and host B are on the same network, host A will then be broadcast an ARP request, as you can see on the screen. So asking for the MAC address of the 10.1.6 10.1.1.6 address. So MAC address, as we have known before, media access control, or it's a physical address of each machine. So now host B ARP request is sent to host B, and host B responds to the ARP request. So ARP request has been sent to the host B, and then now host B responds to the ARP request with an ARP reply containing its MAC address. MAC address could be anything AABB, so that we have seen that's a physical address. Then it will send the host B send the MAC address back to the switch. So host A can now construct a layer 2 frame with a destination of host B's MAC address. So host A host A forwards this frame to the switch, which then forwards the frame to the host B. So um, this is how uh, two host machines which are inside the same network initially communicates and make the confirmation and determination, then to pass over the data to each other. So then we have one more example to look up, that is, now let's consider a slightly modified scenario between host A and host B. Again, host A is on leftmost side and host B is on rightmost side. So here again, similar way as the before the previous example, host A will determine if the 10.1 dot 10 dot 2.1.5 is itself, in this example 10.2.1.5 is not locally configured on host A. So now, so here the network itself is different, so that's the reason host A's IP is 10.1.1.5, whereas host B is 10.2.1.5. Okay, so next, host A, this is our host A, and host A will determine if the 10.2.1.5, that is host B's IP. So host B's IP address is 10.2.1.5, whereas host A is 10.1.1.5. So host A will determine if the 10.2.1.5 address on the same network or subnet as itself. In this example, the subnet mask is as usual. The CIDR is /16. Thus host A's IP address of 10.1.1.5 and the destination address of 10.2.1.5 are not on the same network. So because host A and host B are not on the same network, so host A will parse its local routing table for a route to the destination network of 10.2.x.x./16. So hosts are commonly configured with a default gateway to reach all the destination networks. So now host A has to determines host A determines that 10.1.1.1 address on router A is its default gateway. So now host A has, because a router is the one basically default gateway we have discussed in our previous slides also. Now the default gateway was decided for the host A is 10.1.1.1 on router A. So now host A will then broadcast an ARP request asking for the MAC address of 10.1.1.1 address. So now the host A has sent it to the switch, and through switch it has gone to the router A and requesting for the MAC address of gateway. It's just asking the gateway only. So remaining thing will be done through the gateway because these are in different networks. So this is one network that is 10.2.1. This is in another network that is 10.2, whereas the intermediate piece is our router which is at the center. So this is the gateway for the both the networks. So for this host A, the gateway is 10.1.1.1. So here it is, you can see that this is our gateway. So now host A has sent a ARP request. Now let's see what's going to happen. So now router A responds to the ARP request with an ARP reply containing its MAC address. So basically router A will respond back to the MAC address with the MAC, response back to the host A with the MAC address of router A. So that's it. The host A got the response from the router A. So and then host A can now construct a layer 2 frame with the destination of router A's MAC address. Then responds to the ARP request with an ARP reply containing its MAC address. So router A can now basically create a layer 2 frame destination with a layer 2 frame with a destination of host B's MAC address also, because we have a router A at the center, so it can connect with the host B through the router A. So if you see that animation on the screen, so once the connection is established from host A to router A, then the next task of the router A is to uh, establish a connection with the host B. So now router A has requested for the MAC address of host B, and then host B has responded with the MAC address back to the router, and then once it's sent to the router, now it's all done. Now host A and host B are connected through a router. So note that as a packet is routed, the source and destination IP address remain unchanged. However, both the source and destination MAC address did change. So this is because a MAC address contains no network hierarchy and thus is the only significant on the local network. In this scenario, host A and host B could not communicate directly using layer 2 addressing. At every routed shop, at every routed hop, the source and destination MAC address are registered to reflect the source and destination hosts on the local network. So the source and destination IP address will only be changed if NAT is used. So now let's look uh, look into ARP uh, uh, and understand few more points from ARP. So ARP table, basically here we are talking about ARP table is nothing but address resolution protocol table. Address resolution protocol table. So a host can build an ARP table that contains a list of IP to MAC address translation. So the ARP table is only locally significant to that host. So there are two methods to populate on ARP table. One is statically and second one is dynamically. So either you can have statically ARP table and then dynamically populate ARP table. Either you can statically populate the ARP table or dynamically populate the ARP table. A static ARP entry is created manually on a host and will remain permanently until purposefully removed. More commonly, ARP tables are built dynamically by caching ARP replies. Entries will Cached entries will eventually be aged out of the ARP table. So the aging time will vary depending on the operating system and can range from several seconds to several hours. So now let's look into troubleshooting troubleshooting IP using ICMP. So the Internet Control Message Protocol ICMP we have seen in TCP IP protocol. So the Internet Control Message Protocol is used for a multitude of informational and error messaging purposes. So the following is a list of common ICMP types and codes. So the first one is a dash and just an hyphen for destination unreachable, and 0 network reachable, 1 host unreachable, 2 protocol unreachable, 3 port unreachable, 4 fragmentation needed and don't fragment flag set, 6 destination network unknown, 7 destination host unknown, 9 destination network administratively prohibited, and 10 destination host administratively prohibited. Sorry. So the two most common troubleshooting tools that utilize ICMP are packet internet grouper. Normally we call it as a ping. So ping is a core connectivity troubleshooting tool which utilizes the echo request and echo reply ICMP messages to determine if an IP address is reachable and responding. So ping will additionally provide the round trip time between the source and the destination so usually measured in milliseconds. And a trace route determines the routing path a packet takes to reach its destination. So trace routes will not only identify each router the packet has been forwarded through, but also measure the delay experienced at each router hop. So let's look into this practically. So here we have a VPC, and then okay, it got timeout. Okay, let me log into it. Let me give MFA code, multi-factor authentication code. Yes, it is 4444. Yeah, we are on. So let me get back to the VPC so that I can show some of the things. See, this what I just want to show this route tables. So here you can see the route table. So and then internet gateway. Here you can see the internet gateway, and we also discussed about the elastic IPs. So this is our elastic IP, and we also discussed about the NAT gateway. Here is the NAT gateway. So these are the best examples of NAT gateway. And if you are still confused about that CARD type type of IP. So this is how you can create a CIDR type of IP. So and I just want to show some examples of that. So here also I'll put CIDR. Yeah, uh, if you look into this, yeah, here I have IP based routing. So when I click on when I want to create a CIDR collection type, if you see, here is the CIDR blocks. This is the IP, and then after that, this is version 4, you have 24. So /24. This is our CIDR. So what does it mean? So 24 means, so obviously it says total 24. So 8 plus 8 plus 8. So 16 plus 8, 24. So the first three octets determine or define network, and only one octet determine host. So what does it says? It's a basically class C default subnet mask. So this is an example, and similarly we can have a lot of other examples everywhere. You will find this kind of examples. If you click on elastic IPs, you can allocate elastic IP to that virtual machine, specifically to that virtual machine. Here see I'm in this instance, so I can click on elastic IP and allocate elastic IP for this. See, it automatically gets taken network broad grouper, and then I can attach elastic IP, and this is, yeah, we select Asia Pacific, and my one instance is running there, and this is our VPC. And you see here, come down. So this is my VPC. If you see the address type and CIDR of this VPC, so the Mumbai VPC 172.31.0.0./16. So just explain me what does this mean. So it's here, or else you can see here also. So what does it mean? So it's internet protocol version 4, and then it's 16, so 8 plus 8. So first two octets define network, and then remaining two octets define host. So basically this is class B type subnet mask. So you can have close to 16,000 networks and approximately 64,000 host machines per network. So now let us look into the most underrated topic of networking, that is computer ports. So computer ports and computer port numbers. So port numbers. So what is a port number? A port number is a 16-bit, that's 16-bit numerical value that ranges from 0 to 65535, basically 65,535. So well known ports uh, basically lie from 0 to 1023, and registered ports from 1024 to 49,151, and dynamic ports is three types of port number space. One is 49,152 to 65,535. So now ports these ports can be opened opened and used by software applications and operating system services to send and receive data over networks. So here networks can be LAN or WAN WAN. So that employs certain protocols, example TCP and UDP. So for example, we use 8080 for 8080 for HTTP web-based plain text surfing, and 443 for HTTPS web-based encrypted websites in our daily work. So 80 for HTTP web-based plain text type of application, and 443 which is secured HTTP connection. So HTTPS is 443, that port, and then 80 for unsecured application to be run. So to conclude, a port is a logical form to identify system activities or various network services used to create local or network based communications. So now the next question arises, what are the functions of ports? So when interacting over the internet, TCP and UDP protocols make connections, recompile data package after the transfer, and then deliver them to applications on the recipient's device. For this handover to work, the operating system must install and open gateways for the transfer. So each door has a unique code number. After transmission, the receiving system uses the port number to determine where the data should be sent. So the port numbers of the sender and receiver are always included in the data packet. So ports are assigned sequential numbers from 0 to 65,536. So some of these codes are standardized, meaning they are assigned to certain users, since code numbers are universally recognized and permanently assigned. So these standard ports are also known as well-known ports. And registered ports are those that organizations or software developers have registered for their applications. So registration is handled by the Internet Assigned Numbers Authority. We have discussed about the same in our earlier slides. So IANN NA, that's Internet Assigned Authority. So, Internet Assigned Numbers Authority, a diverse selection of dynamically assigned port numbers is also available. So, for example, when viewing websites, browsers use the ports. After that, the phone number is free again. So, but the thing is, why is it important to know about these ports? Uh, any security researcher, bug bounty hunter, or anyone working with the service configuration would benefit from this. So, knowing how to do more through scans such as a version detection or known vulnerabilities for ancient services that are still operating in the infrastructure, especially when using tools like Nmap, is handy when getting to know these protocols and services. So now let's look into the topmost or 50 most 50 significant ports in this forthcoming slides. So the following are some of the most common service names, transport protocol names, and port numbers used to differentiate between specific services that employ TCP, UDP, DCCP, and SCTP. So let's look into various services which runs at default port number and then their protocols and description. So we will begin with 7, that is Echo. Service name is Echo, and the transport protocol it uses is TCP or UDP, whichever is possible, and the description is known as Echo service. Then after that we have port number 20. So port number 20, uh, FTP data, the file transfer data, file transfer protocol data is the one which service is the one which runs at the port number 20, and transport protocol TCP and SCTP. And the description about this file transfer protocol data transfer. Then we have FTP service. Again, FTP service is nothing but file transfer protocol control connection, and this service runs at port number 21 and with a transport protocol TCP, UDP, and SCTP. So let's look into few more services and significant ports. So at so next we have SSH SCP. So basically SSH SCP is secure shell, secure login file transfers and port forwarding. So this service basically runs at port number 22 with transport protocols such as TCP, UDP, SCTP. Then we have 23 20. Then we have telnet protocol. It's an unencrypted test communication, and this service runs at port number 23, and this service runs at port number 23 with transport protocol called as a TCP. So then we have SMTP. So it is simple mail transfer protocol used for email routing between mail servers, and this simple mail transfer protocol runs at port number 25, and it uses transport protocol such as TCP. So then after that we have DNS, which is domain name system name resolver, domain name system name resolver, and this service DNS service runs at port number 53, and it uses transport protocol such as TCP and UDP. So then after that we have TFTP, that is trivial file transfer protocol, and this runs at port number 69 with the transport protocol UDP. So and then what we have is HTTP. So HTTP service is nothing but hypertext transfer protocol and uses TCP in version 1.xn2. So HTTP 3 uses a QUIC, a transport protocol on top of the UDP. So and this HTTP service runs at port number 80 and uses transport protocols such as TCP, UDP, and SCTP. Then we have Kerberos, a network authentication system, and this runs at port number 88 with transport protocols such as TCP, UDP. Then we have ISO TSAP and ISO Transport Service Access Point, ISO TSAP, that's ISO Transport Service Access Point Class 0 protocol is which runs at port number 102 with a transport protocol as TCP. Then we have POP3, so this is Post Office Protocol version 3, and which runs at port number 101, so 1110, and transport protocol for this POP3 is TCP. Then after that we have Microsoft EP map. So Microsoft EP map endpoint mapper, also known as DCE or RPC locator service, used to remotely manage service including DHCP server, DNS server, WINS, also used by DCOM, and this service runs at port number 135 with the transport protocol TCP and UDP. Then after that we have NetBIOS NS. So NetBIOS name service used for name registration and resolution. So uses 137 port number and transport protocol TCP and UDP. Then we have NetBIOS SSN. So NetBIOS session service runs at port number 139 and uses TCP and UDP as transport protocols. Then we have IMAP4. So IMAP4 is nothing but Internet Message Access Protocol. Internet Message Access Protocol, management of electronic mail messages on a server, and this runs at port number 143 with the TCP and UDP transport protocol. Then we have HP OpenView. So HP OpenView is nothing but HP data alarm manager. So it can run at 381 and 383 also at two ports, and it uses TCP and UDP as transport protocol. So then we have HTTP or SSL, so hypertext transfer protocol, which is a secure one, HTTPS. So that's what we call it as a HTTP over SL. That means a secure one. So uses TCP in versions and similar to HTTP. So it uses 443. The secure HTTP secure uses 443. Normal HTTP uses 480. So and it uses as usual transport protocols such as TCP, UDP, SCTP. So then we have Kerberos, and this Kerberos is used to change or set the password, and the port number for this is 464, and then TCP and UDP are the transport protocol. Then we have SMTP over TLS or SSL, SSM. So it's like authenticated SMTP over TLS or SSL certification. So this is called SMTPS. So it's a secure one then compared to the normal SMTP, which is not that much secured. So in normal SMTP is 225, and this one is 465 with the TCP transport protocol. Then again we have one more SMTP, but this time it's an email message submission. This is at 587. Then we have Microsoft DCOM, so HTTP RPC EP map, remote procedure call over hypertext transfer protocol, often used by distributed component object model services and Microsoft Exchange Server, and it uses a port number of 593 and transport protocol of TCP UDP. And then LDAP over TLS or SSL. So it's a lightweight directory access protocol over TLS or SSL, and it runs at a port number 636 and transport protocol of TCP or UDP. So then we have MS Exchange. So MS Exchange routing, and it runs at 691 with a transport protocol TCP. Then we have VMware server. It's VMware ESXi, and then there is no transport protocol because it is unofficial, but it can be run at 902. Then FTP over SSL, we have seen FTP unsecure one, but you can have a secure one over SSL. That's FTPS. We call it as FTPS protocol data, and FTP over TLS or SSL, which runs at 989, and similar to the FTP or SSL. And same FTP or SSL can also run at 990. So both follows transport protocol of TCP and UDP. So then we have IMAP or SSL. We have seen IMAP 4, and similarly IMAP 4 or SSL. The description remains same, but it's a secure one. So it takes TLS or SSL with it. So that's the reason it's secure, and then it runs at port number 993 with TCP. Then we have POP3 or SSL, same again, this is also secure POP3, and it runs at 995. So, and after that we have Microsoft RPC. So Microsoft operating systems tend to allocate one or more unsuspected publicly exposed services, probably DCOM, but who knows, among the first handful of ports immediately above the end of the service port range 102 plus. So this runs at 1025, and then we have OpenVPN virtual private network. So this runs at 1194. So then WAST is one more service, which is WAST encrypted file sharing program, which is unofficial, and it runs at port number 1337. Then Cisco VQP, it's Cisco VLAN query protocol VQP, so it runs at 1589. Then Steam, that's Valve Steam client, uses port 1725, and cPanel, the cPanel default uses 2082. Then RADSEC cPanel uses 2083. Oracle DB. So Oracle DB is nothing but Oracle database listening for insecure client connections to the listener, replaces port 1529, and it uses 2483. And then Semantic AV uses 2967, and Xbox Live and games for Windows Live, and it uses support number 3074 with TCP or UDP as a transport protocol. Then we have MySQL. So it's MySQL is nothing but a database system, and the port number that where MySQL runs is 3306 with the TCP transport protocol. Then we have World of Warcraft. This runs at 3724. Then Google Desktop, it's unofficial, but it can be run at 40064. It has its it has a port allocated for even Google Desktop. Then we have Postgres SQL. So for Postgres SQL database system, so you should have a port number of 5432 with the transport protocol TCP. So then more so RFB VNC server, this is virtual network computing remote frame buffer RFB protocol, and 5900 is the port number. And for IRC, it's Internet Relay Chat 6665 is the port number. And for BitTorrent, so BitTorrent is a part of the full range of ports used most often. So 6881 is port number for the BitTorrent. And QuickTime is unofficial, and the port number is 6970. And for Kaspersky AV, it's an antivirus. Kaspersky Antivirus Control Center. For this, we have allocated to 8086 if it is through TCP, 8087 if the transport protocol is UDP. Then after that we have VMware server, that is 8222. Then we have PDL. So PDL, data stream used for printing to certain network printers. So the port number that it takes is 9100. Then we have backup exec, so that's 10,000. And netbus, so netbus is unofficial. So netbus, a remote administration tool, often Trojan horse, so 12,345. Then sub 7 is sub 7 default, it's unofficial, and 27,374. And back orifice unofficial, so back orifice 2000 remote administration tools. And PostgreSQL, as we have discussed earlier, 5432 with PostgreSQL database system, and then follows TCP transport protocol. So with this, we are concluding third module of iDevOps for you. So we have closed the networking layers also. So we have come to an end of networking topic. I hope you enjoyed. So we have covered most of the important topics that are related to networking in depth, and with practical demonstration. I hope you enjoyed it, and then keep liking my content, and keep watching my content, and keep subscribing, and spread it to your friends. And I will meet you in another module of this course.